of Managing Director, Semiconductor Products Group, Applied Materials in India. He's an alumnus of our department, so it's very nice to have him here. Thank you once again, Dr. Suraj, to be having agreed to come here. He heads the Semiconductor Products Group for Applied Materials India and is based in Bangalore. In this role, he focuses on SPG strategic objectives in India, planning and growing a customer-focused organization, growing local leadership talent, enabling collaboration across India and Asia region, and strengthening university and ecosystem partnerships. Dr. Rangarajan started his career in Applied Materials, Santa Clara in 1997, where he held different roles ranging from process engineering, technology, program management, and product marketing for thin film deposition and metallization for interconnect silicides, and novel memories. He moved to India in 2007. I also moved back to India in 2007 and joined as a faculty member here. So nice to see that you were back also in 2007 to head the Sunfab group of, for Applied Materials in India. Later, he headed the engineering group for dielectric deposition. As the India CTO, he worked on materials engineering-driven inflections to develop and commercialize new technologies. Dr. Rangarajan holds a BTech degree from IIT Madras in metallurgical engineering. We are proud of you that you are a part of us. And earned his master's and PhD from the University of Texas at Austin in material science. He has over 15 US patents and holds more than 20 publications. Thank you, Dr. Suraj. Welcome on board.
Okay, wonderful. Good morning, and hope all of you stay safe today. I know it's going to be raining. I luckily came in last night, just before it started, and I hope to leave tonight before it, hopefully they're saying it'll end. All of you can hear me, right? Yes. I don't want to stand next to the mic. It's a small crowd, so we'll try to keep it close. So we'll be here again on 28th. This is the 35th year after graduation, so we have a reunion. So our batch will be here later this month. I'm glad to be back in IIT Madras. Oh, okay, good. Okay, I will use the mic. Okay, so good morning, and I will try to treat this more as a informational session on semiconductor, right? What is happening in semiconductor, what's happening in semiconductor in India, and where materials engineering can play a role. And this is something where we are working with the materials community in India to do stuff. So I'll show a few things that Applied Materials is doing. We are working, we have our colleagues here, Gopi, Sampath, and Gayatri. So there are programs that we are actively working with the materials community. I'll talk about some of the things that we are doing and how the materials community can help us with some of these challenges. A disclaimer, a lot of these are my views and don't constitute necessarily what the company has to say. A few things I'll talk about applied materials. Not many in the audience may know about what we do. I'll talk about materials engineering, how we view that, why that's so important for the industry and in semiconductors, and a few things that we are doing in terms of how we collaborate with the ecosystem. So Applied Materials is a Fortune 500 company based in California. We recently announced our results, about $27 billion. We spend a lot of money in R&D next to life sciences and pharma. So this is the industry that puts a lot of money back into R&D. So about the research R&D intensity is about 16%. Pharma, life sciences is about 18-20%. Very IP rich, close to about 20,000 patents, and very global. More than 35,000 people in 24 countries. So this is a sort of list of all the different tools. So we are an equipment company. We make machines. So if you look at the left-hand side, these are all the different process equipment that goes into a semiconductor industry. Each one is a process step. So you are either depositing, removing, polishing, changing, modifying material that makes semiconductors. And on the right-hand side, these are the drivers for the industry, right? Why is this industry growing? I'll talk a little bit about numbers, right? What is driving that is the data center AI. So every time you post something on Facebook or Instagram or something like that, that picture goes and resides in a server, and that is one of the, and your Google search or something, that is the biggest driver today. There is power, renewable energy, communication, sensors, and a lot of the auto industry, how it's moving from the conventional ICE to EV and associated, even the driverless cars and stuff like that. And AI and IoT, these are the big drivers. So I'll talk a little bit about what they do and why you need changes, new materials for that. We've been in India for more than 20 years, 5 locations, mostly in Bangalore. I came to India in 2007. At that time, Applied Materials was close to about 700-800 people. Now it's about 8,500 people. It's about 10x increase in terms of numbers. Like with all companies, it started with back office, back end stuff, and now there is a lot more R&D. The team in Mumbai does a lot of R&D, advanced R&D for the company, and Sampath's group is looking at how we can work with the ecosystem, especially in ceramics, and look at ways that we can find new suppliers and develop and strengthen that supplier ecosystem for semiconductors. So I'll talk a little bit more about that. We have built infrastructure in India over the past few years. When I came, there wasn't much in terms of lab or ability to do anything. But now we have a lot of infrastructure. So this allows us to also collaborate with both the academia here and industry here to do things. Mostly engineering type infrastructure, but we are also building a lot of R&D infrastructure, and we are building process capability so that we can actually synthesize new materials, test, characterize new materials. So this is probably if you take away one thing from this talk, this is it. So today, the semiconductor industry is at about $500 billion, right? Somewhere the dot in the middle over there. This took more than 50 years. Applied Materials started in 1967, so it took more than 55, 56 years to get to this point. The next jump, right, the 500 going to $1 billion is expected in the next 5 years. So that is going to be the biggest driver, and that's going to change everything, and that's where we need more people from the materials community and the mindshare to help with this, right? And all of this is getting driven by AI, different kinds, different versions, different embodiments of AI. So we believe that that's what is going to drive a lot of this growth. And that's sort of different from what got us there. I think all of you are aware of all the other, we had mainframe PC and your mobile and all that, which got us to this point. The next doubling is going to happen primarily from AI. So another just primer for people who just to understand semiconductor. So the left-hand side, this circle is a 300 millimeter wafer. So think of that as a large size pizza. In that, we are looking at, there are close to about 400 dies. Each die is probably a centimeter by centimeter. That's that blue square. Inside that square, you have like what looks like a multi-story building. So the way this is created, you take that die and then you strip off everything other than the metal. So that is the copper wiring. So at the bottom of that is the transistor. This is like a foundation of your apartment, multi-story building. And that all that copper wire takes that signal out to the top. And that's what you can then measure and then sort of communicate with. So this is your, what goes into the chip, right? So the top part is all just conducting material, the bottom is your transistor. And if you take that transistor, the, the top part, we are talking about kilometers of wiring. So just that part takes about, it says about 100 kilometers. This is about 15 layers. We used to have 4 or 5 layers, and that's come to about 15 layers right now. And lot of connections between these different elements to get there, right? This is all that the semiconductor industry enables. The bottom part is the transistor. So this is a new gate all-around version of the transistor. You have about 50 billion of such transistors, and this is where the real materials engineering comes in. So what was sort of easily done a few years, couple of decades back, now requires very, very, very close collaboration between different kinds of disciplines. There is materials engineering, there is physics, there is chemistry, and there is device engineering, electrical engineering, all that which goes into making that happen, but primarily materials. Materials and interfaces, that's what drives a lot of this. And also as you shrink, the interface component of that becomes bigger and bigger, and you're talking about how you can do it at an atomic scale. Now going back to the, so this is just a blow up of that. So this is individual transistor, and just in that space, there are different materials that are stacked, right? So what makes this complicated is this. You can do one of these in the lab. You can make them once. You need to make each individual transistor. You need to make a die of that. You need to make 400 dies of that. You need to make 25 wafers of that in many 50 fabs across the world. And they all need to perform the same. That is the challenge that the semiconductor industry has. It is not making one. Everybody can make one. Can you make it at atomic scale where all of these perform? Your edge die on this side and the die on that side behaves the same, so that the iPhone 16 that you have performs the same as your neighbors, right? That is the industry challenge of making the performance the same, and that's where materials engineering is a big part, because what we are talking at atomic scale needs to be across the wafer. Across 300 millimeter wafers, you should have the same performance of all these materials. So this is what we call materials engineering. The ability to create these materials. You're depositing different kinds of metals and dielectrics and all that across a large scale. You are then removing them. So these are millions of holes that are done at each one of these in order to make those contacts with very high aspect ratio, and then also keeping the structural integrity. After you do all this, that you're putting in thousands, millions of these holes, that structure needs to be strong and it needs to be reliable so that your phone works for more than 2 years. And then the third part of it is the inspection. So every time you, for every fourth or fifth step, so there are close to about 1,000 to 3,000 steps that are there when you make a semiconductor. Every fifth or sixth step you inspect. And when you inspect, you're checking to see that there is no defect. If there is a defect, and especially if it's they call it killer defect, it will impact the performance of the die. Then you have to either remove the wafer, stop the process, or do some change so that when you, otherwise you're going to sort of impact millions of dollars. Each 300 millimeter wafer by the time it's done is worth millions of dollars. So you want to keep inspecting to check that there is no defect. So this defect, just to get a sense, if you fly a plane about 5,000 feet on top of New York, you will be able to see a penny on the street and you can see an ant on the penny. That is the level of resolution that you need in order to be able to see a defect, because you're seeing real time. There's a 300 millimeter wafer and you're inspecting the entire thing and looking for nanometer defects on that. So all of these are very sophisticated engineering challenges that the industry has been able to resolve over the past 50 years and will continue to do so. And then the scale, if you look at, there is a person standing there. This is a system that's used in our display. So if you look at, to be able to make a glass of this size and deposit material on that, different layers and all that, to make your LCD TVs, OLED TVs and things like that. This is the kind of equipment. Even this you have to do at atomic scale. You have to make these transistors again at atomic scale, and you need to be processing at very large geometries. And in some cases we also do this roll-to-roll processing. So you need to be doing it while the web is moving. So now what does all this materials engineering enable? It can enable many industries. There is, in this talk I'm going to continue to focus only on the semiconductor stuff, but I also wanted to bring about the different things that this has enabled beyond semiconductors. There is life sciences. So if you look at materials, stents and things like that, the coatings that go on that, there is materials engineering that enables that. There is digital manufacturing. I know that in this conference you're talking about additive manufacturing. There is energy storage. A lot of the thin film for battery is being done using materials engineering that was developed for semiconductor. So the lithiation process, coming up with the lithium anode and the scaling of the batteries, uses a lot of the semiconductor manufacturing techniques. AR, VR. So the next level of display after LCD and OLED, we believe that there will be micro LED. We believe that the applications of this, making the right kind of waveguides, and AR, VR for this will be the next inflection. And then of course solar is something that's already happened. I was part of the solar, and actually the price reduction in the case of solar has been even more than in the semiconductor industry. Okay, continuing on, just this is just from a thought experiment kind of thing. If you try to make your cell phone today using semiconductor technology that was available in the 80s, it would cost millions of dollars and would consume a lot of power. So imagine they use this kind of technology to launch rockets and all that, which you can right now operate with your hand. The biggest driver in the semiconductor industry is something called Moore's law, right? where the number of chips that could go into a specific area would double every couple of years with about the same cost. So this drove the industry for about 40, 50 years, right? You could continue to keep shrinking and get more performance. I remember long time ago when we would go looking for computers, you would only look at megahertz. How many megahertz? 300 megahertz, 400 megahertz, 500 megahertz, the speed, right? And that stopped at some point. So the other change is just from a pure materials itself. When I joined when I was a grad student, we used to use few materials. You could count in your fingers, few more in the 80s and 90s. And now almost the entire periodic table is used, and a lot more materials. Silicon carbide, gallium nitride, you will start seeing a lot more compound semiconductors entering the picture soon. And variations of these, right? Not just materials, now silicides, nitrides, oxynitrides. So the entire semiconductor industry has been driven by this. How can you take materials and how can you make them in the right way with the right kind of properties at the right scale to get the kind of performance and reliability that you want. So materials has driven everything that we have done in semiconductor. So this, again, just from a Moore's law perspective and where we stand with that. So I will show in the next couple of slides that Moore's law is slowed, plateaued. One of the things that is replacing Moore's law is something that we call PPACT, which is power, performance, area, cost. So this Moore's law is basically area cost. The area goes down, cost stays the same, you get more performance, and that's what has made the industry go. But now, when you go to buy a laptop, nobody cares about megahertz. Everyone cares about, will the battery run for more than 4 hours? Will my screen have display? Will my performance meet what I need? So this performance and power consumption is a driver. And more with mobile applications and everything. How long can my battery last and give me the performance that we need is the biggest driver. So if you look at this in terms of performance, so just the raw performance has stabilized. So you are not getting higher performance right now because in order to get that performance, the power consumption is a lot more, people are not willing to pay for it, and the cost is also going up. So that is where the Moore's law is more, it's not a technology law, it's more a business law. Moore's law decided how much money was being spent for products that were being made. The other part of it is on the right-hand side, the time it takes. So you buy a phone every couple of years, and earlier Intel used to have that tick-tock cycle. Every 2 years they would come up with a new chip that would then go into a desktop or a laptop, and then the performance would change. Now going from one node to another is taking longer because the kinds of materials, innovations, and other things that you need to do to get the performance that you need, the time is taking longer. So that this combination of these is why we are saying that Moore's law has stabilized or dead. The biggest driver now is this. If you look at the left-hand side, it's a Google search, whatever you type on your computer. On the right-hand side is a ChatGPT search. Right now, it's about 13x more energy intensive to use AI to do the same search. Whatever you type in, if you ask ChatGPT to do that versus your Google search, you're going to consume more energy, and more people are going to the right? If you ask any kid to do their homework right now, they go to ChatGPT. So the problem, this conference is about sustainability. The problem is that we are also going in the wrong direction in terms of sustainability. We are making available these things which are going to consume more energy. And there is a problem with that. If you continue down this path, there isn't enough energy. So I know that companies are already putting their servers in Iceland and in places where they can have natural cooling, right? The energy consumption and the cooling of the servers to drive the AI growth is one of the biggest problems today. So how can you bring down the energy per bit is one of the biggest challenges in the semiconductor industry. And that's where materials is going to play the biggest role. We will need changes in terms of materials, architecture, and how we build chips and how we use chips so that we do not go here. Otherwise, right now, a big portion, I think the servers right now, the amount of energy they consume is about the same as small countries, right? The kind of energy consumption, it cannot scale the same way. So now a few more things about how the industry works in terms of materials. So Gopi and his team and Gayatri, they look at materials, they look at synthesis of materials. Can I take material A, material B, make a compound, and can that compound be used in semiconductor? Let's suppose you are trying to come up with a new dielectric, new material, new conducting material. So if you need to do this, then you need to characterize this, make sure that it works. Are you able to synthesize, get it in the right format and all that? And then put it inside a process chamber and check if it works. So on the left-hand side is like a representation of a semiconductor system. So this has about 7 different process steps. You can take that as ALD, CVD, PVD, cleaning, etching. So a wafer goes in, it goes through all these process steps, and then inside each chamber, you monitor what is happening, and then try to figure out what you can see as your final film, right? So far, the industry has been doing the left-hand side. You make, you test, you make, you test, you make, you test. The question is, can we do the right-hand side? Can we make digital twins of these chambers? And based on the data that we have, can we try to figure out how we can use this information and try to sort of formulate some of these films and compounds and all that from a digital twin? So that's something that the industry is looking at. This is one of the ways that we will try to scale things going forward. It will also help the industry converge on new materials faster. So this is how that process will go. We will come up with a new material. We will then test it on an equipment, both through physical and digital twin. Then we will then integrate up and down. So these films don't exist on their own. They are built as a stack. So the previous film and the next film interaction interface also matters. Then you put it together in a factory, and then finally you make a product and see if it works. So this is how this flow works. The left-hand side is where we are trying to engage with the materials community to come up with new materials. And this is where a lot of the interaction is with academia in terms of, can we come up with new materials on the left-hand side that will give us more options on the right-hand side. So I will skip a few of these. So this is basically a representation of whatever I said so far in terms of what goes through this. We prepare the surface, interface engineering, we deposit different materials, and we do materials modification, and that's how we make this one example of device. Okay, now coming to the last topic that I had in terms of how we engage with the ecosystem here. So left-hand side is a representation of one of the equipments. We call this Vistara. It can be any equipment. This equipment has more than 100,000 parts. And I think the engagement that we are looking from this community is this requires lots of things to go in, which is robotics, vacuum, optics, ceramics, thermal, seals. A lot of these are raw materials. How can they be engineered to perform in this to deliver the kind of properties that we want from an engineering performance? This has nothing to do with the semiconductor part, just the machine. The machine has to function. How can we make? And here is an example. So Gayatri's team does this. So this is like a process chamber. Inside that chamber, we have plasma. You need materials that can withstand the plasma, not produce defects, and deliver the kind of film properties that we need. So, and this is something that the team here is working with the ecosystem and with supplier vendor partners on how to do this. The next couple of slides, I'll just talk about how industry is trying to make this go faster. On the top is our traditional way of engaging with the ecosystem, with customers, with suppliers and others. We do foundational research, then we try to put it in the system. As I demonstrated, we try to make devices out of that, and then finally it comes out as a chip. This takes more than 10 years for any chip to happen. How can we do that faster? By engaging with the customers and suppliers ahead of time in this early approach. So in Santa Clara, we are building this network called EPIC, where we are going to bring customers and suppliers inside to work with us to develop the next generation chips. This is what we are planning in Bangalore, where we will work with suppliers and academia to do the same thing in India. For the semiconductor industry that's coming in India, new materials, new parts, new components, new coatings, how can we work with the ecosystem to make this happen? So this is sort of our support for the semiconductor system that will come here, and also we are trying to bring global partners in here. So Air Liquide and then MKS, and there are some Rockwell. There are companies that serve the semiconductor industry. How can we have them come and work in India to support the global semiconductor industry and also the India semiconductor industry? My last slide. So the way Applied thinks, think big, test small, learn quick, fail fast. That is sort of the way we are trying to work so that we can quickly do multiple learnings. We also have a ventures arm that works with different companies. We have global university partnerships. We work with research institutions, and we have our own labs where we do a lot of R&D. So with that, I wanted to conclude that materials engineering solutions are required not only for semiconductors but for many other industries. We've been a pioneer in that. We work with the ecosystem partners to make it happen. And for the upcoming semiconductor industry in India, we will work with the ecosystem to support whatever is required to make this happen. And with that, I'm open for any questions on anything that I talked about.
Thank you very much, Dr. Suraj, for giving a wonderful perspective about the semiconductor ecosystem in the country. May I now ask if there are any questions from anybody?
Nice presentation.
Thank you.
So my question to you is that, so people are now going up to maybe 3 nanometer node semiconductor. So when you look at the materials ecosystem, supply chain, you have a projected 50 plus materials, which node size which you are looking for? For example, up to 28 nanometer, no more material, whichever is available.
Sure. So I'll talk from an India perspective, right? Anything that the semiconductor industry is trying to do in India is what we call legacy nodes, right? 28 nanometer and below. So I don't think first we have infrastructure and capability and expertise for the advanced nodes. And second, I don't think we have the money. Fab for the 3 nanometer is in the order of $10 to $15 billion, which can be used, better used. So I think India a lot, and there is enough applications that can be done at the legacy nodes. So I think a lot of our effort, priority will go into legacy nodes, and where I think we can do a lot of differentiated things. Renewable energy related stuff, right? Inverters, there are lots of technologies which can be well served with legacy nodes. And they also require new materials. They require a lot of things that this ecosystem needs to develop. So, any other questions?
Are there any other questions? One more? Yeah. If not, thank you very much, Dr. Suraj, for making your time for coming here. Thanks a lot. As a token of our appreciation, we have a very small memento to you, and I would like to request both the chairman of the conference and as well as the vice chairman of the conference to come and hand over the gift to. Please. Sure. Thank you so much. The next session is a SPARC-sponsored workshop. So the next session is on additive manufacturing of advanced ceramics. It's a workshop sponsored by the Scheme for Promotion of Academic and Research Collaboration from the Ministry of Education. Me and Dr. Emmanuel Ionescu are leading the projects from India and Germany. I would now request Emmanuel to come here and chair the session. So he's a German partner, so I would like him to do the session.
Thank you. Welcome to this session on additive material of advanced ceramics, and we will have quite exciting talks. It's a sort of Indo-European session. We have European contributions and Indian contributions. And we will start with the first keynote lecture, which will be given by Dr. Samuel Bernard from University of Limoges and CNRS. And without further ado, please, Samuel, stage is yours. We're looking forward for your talk.
Thank you, Emmanuel. Can change here. It's not a problem. Yeah. Okay. Okay. Good morning, ladies and gentlemen. So first of all, excuse me. So thank you, Emmanuel, for your nice introduction. And I would like to thank the organizing committee for giving me a chance to speak about the 3D printing of polymer-derived ceramics. Especially, it will be dedicated to the design of stoichiometric silicon carbide. This work is done at the Institute of Research for Ceramics, belonging to University of Limoges and CNRS in France. So my talk will be shared into 3 parts. As an introduction, I will speak about the 3D printing of silicon carbide, which is highly promising, but also highly challenging. And we will speak about sort of solution to tackle such issues. I mean, the polymer-derived ceramic route that will be coupled with 3D printing, especially fused deposition modeling, to prepare 3-dimensional silicon carbide parts. Then I will go through the main results of this presentation, especially the design of silicon carbide by granule-based fused deposition modeling of polycarbonylene to lead to stoichiometric silicon carbide. And I will finish by some conclusions and perspectives. So as probably you know, 3D printing of silicon carbide is highly promising, an hot topic, especially from industrial partners. Mainly for such a region, you can prepare customized pieces with a reduced material waste. And this is very important for an industrial partner. But it is also highly challenging because it requires various post-3D printing processes. I mean, you need to combine several sintering methods to reach the materials you expect. I mean, you should combine 3D printing with sintering methods such as liquid phase sintering, liquid silicon infiltration, or polymer impregnation pyrolysis. So this means that this is a quite complex process. And the current work is to simplify this process, and maybe one of the solutions can be the polymer-derived ceramics process. So this process starts with pre-ceramic polymers. Some of them can be commercially available, and then you have successive stages: cross-linking, redistribution, ceramization, and crystallization to lead to polymer-derived ceramics as advanced ceramics, mainly in non-oxide system. Such materials, especially the pre-ceramic polymers, are very interesting because you can shape these pre-ceramic polymers before the cross-linking using 3D printing with such technologies. But this is very interesting only if you can control the volume shrinkage that occurs during the polymer to ceramic conversion, because you have in general a large volume shrinkage that can reach 60 or 70%. And if you don't control this volume shrinkage, you collapse the shape which has been imposed at this stage. Okay, so it is very important to consider this aspect to prepare materials starting from pre-ceramic polymers. As additive manufacturing technology, one of this one, I mean materials extrusion, is probably one of the most interesting because it's a cheap technology, but the resolution is maybe not the best one compared, for instance, to stereolithography. And you can prepare durable pieces, especially that are used in harsh environment. And as material extrusion technology, there are 3 methods which are proposed here, and all of them rely of a thermoplastic compound that flow as a melt into a nozzle. So there is this method using a filament that it melt in a nozzle, and these 2 methods that use directly granule, I mean the powders. And we mainly focus on this technology because they represent a simple technology, especially compared to this one, in which you need to prepare the filament. Okay, so we particularly focus on these 2 technologies, especially this one using a serang. And such technology requires some specific properties for the compound you want to melt. First, this compound should display a shear thinning behavior, which means that the viscosity decreases with the shear rate you impose during your 3D printing. And this viscosity should be appropriate to extrude your materials and to keep the shape which at the exit of the nozzle. In general, you need a viscosity between 1,000, 10,000 Pascal per second. Once your filament has been extruded, you should have a rapid increase of the viscosity to retain the shape of you plan and to avoid the collapse of this shape. And then, at the end, the mechanical properties of your materials, I mean, the filament should be quite high to support the successive printed filament which are added on the first layer. So it's not quite easy, but we can control such aspect. But now, may we print 3D silicon carbide parts by granule-based fused deposition modeling of pre-ceramic polymers? Yes, we can. If you consider organosilicon polymers, especially polycarbonylene, but not maybe the conventional one you probably know, which is used to prepare silicon carbide fibers and which has been proposed in the 70s by Professor Yajima, and such fibers are commercially available nowadays. So this polymer, polycarbonylene or PCS, is quite nice because it is a thermoplastic, so it could be used for granule fused deposition modeling technology, and it delivers silicon carbide at relatively low temperature. I mean, 1,000 degrees C, you can produce silicon carbide, which is amorphous, but you can produce silicon carbide. So, do you think that this polymer can be interesting for granule-based fused deposition modeling? In fact, not, because its temperature of extrusion is quite high, 300 degrees C, and the yield of silicon carbide is quite low, 55%. Therefore, in general, you cannot produce 3D silicon carbide parts using this polymer. There is one paper that used this polymer, and you can see that it mixes with polypropylene just to decrease the temperature of extrusion of the mixture from 300 to close to 200 degrees C, and these authors could prepare three-dimensional silicon carbide parts. However, despite the fact that the resolution is quite high, you can see that the piece is black, which means that you have a lot of free carbon in your polymer. So now let's move to our results that consist to prepare stoichiometric silicon carbide from polycarbonylene by granule-based fused deposition modeling. We consider a commercially available polymer, which is proposed by Starfire System, this polymer, which is called SMP 730. We measure the composition, and as you can clearly see, you have a large excess of carbon in this polymer. This is clear on at the top on the right, and this is due to the presence of aromatic group in the structure of this polymer. Because of the presence of this aromatic group, this polymer is thermoplastic and it displays an extrusion temperature around 100 degrees C with a yield which is close to 70%, which is very advantageous compared to the conventional PCS that display a too high temperature of extrusion and a relatively low silicon carbide yield. However, this carbon-rich PCS has three main drawbacks. The first is display a too low viscosity as a melt. If you remember, I mentioned that you need a viscosity between 1,000 and 10,000 or 15,000 Pascal per second. Here, as a melt, the viscosity is too low, and the glass transition temperature also is too low. Therefore, you can extrude, but you collapse the shape at the exit of the nozzle. The second drawback, that despite the fact that it displays a quite high yield, 67%, you can see that you form foams at the end of the pyrolysis because you release aromatic groups during the pyrolysis, therefore you create a large part of porosity in your materials. As a third drawback, as I mentioned, this polymer is a carbon-rich PCS, therefore you form a carbon-rich silicon carbide at the end of your process. You can see the carbon content in the material, which is which is quite large compared to silicon. So now, how to tackle such drawbacks to prepare our stoichiometric silicon carbide with a granule-based FDM process? So in fact, we use this polymer as a binder, and we add the first silicon carbide powders inside to increase the viscosity as a melt, and also to reduce, of course, the polymer content and avoid or limit the quantity of pore in the final materials, and at the end, to reduce the volume shrinkage that is imposed during the polymer to ceramic conversion. Then we added silicon powders to react with the excess of carbon at high temperature and form silicon carbide in our process. Also, such silicon powders can limit, in addition, the volume shrinkage that occurs during the pyrolysis. And then we perform a sort of thermolysis process at low temperature, 120 degrees C, for 4 hours, to link this carbon-rich polycarbonylene with the powders and to increase the gas transition temperature to close to 70 degrees C, and forming this polymer. With such processes, we, of course, were able to increase significantly the viscosity of the materials as a melt. You can see that it still displays a thermoplastic behavior despite the presence of powders in its structure, and you can see that the extrusion domain is between, I would say, 80 and 120 degrees C. If we go in more details into the rheological properties of such a polymer, you can see here that it displays a shear thinning behavior. I mean, the viscosity, which is on the right side, decreases with the oscillatory frequency, I mean the shear rate. That means that when you impose a high shear rate, the viscosity is sufficiently low to extrude these compounds through the nozzle. If you have a look on the elastic and viscous moduli, elastic J prime and viscous J double prime, you can see at a certain oscillatory frequency there is a crossover. So the viscous modulus is above the elastic one. This is a domain to extrude your polymer. So this means that this polymer can be extruded at quite high shear rate during 3D printing. And of course, when you extrude this polymer at the exit of the nozzle, you should have another crossover. The elastic modulus should be above the viscous one to form rapidly a solid material at the exit of the nozzle. Here is a video of the process. I hope it will work. Yes, it works. So this is not the real speed, of course. You can see that, so we extrude this polymer at 90 degrees C with a nozzle with a diameter of 400 microns, and we can form these nice pieces. You can see that we have some part that exit from the piece, which means that we are in an over extrusion, so maybe too high compared to the real extrusion temperature. So we can form these nice pieces. Okay, and then once this piece, which has been prepared in air, you should keep in mind this, whereas such polymer can be sensitive to air. So we prepare such piece in air, and then we perform the pyrolysis at 1000 degrees C under argon, so from the left to the right. So we have a very low volume shrinkage, less than 10%. It is because we introduce powders inside, I mean silicon carbide powders, which are inert during the pyrolysis, but also silicon powders that will react with free carbon, not in this temperature domain up to 1000 degrees C. Then, after 1000 degrees C, we perform a heat treatment to 1400 degrees C to deliver these pieces that display a ratio between silicon and carbon of 1, because if you have a look on the XRD, So you have the temperature, the red XRD pattern is the materials prepared at 1000 degrees C. You can see that you have mainly silicon because of the diffraction of silicon powders which are distributed in the material. Then when you increase the temperatures at 1400 degrees C, you convert these silicon powders into silicon carbide, which means that silicon react with the excess of carbon which is produced from the polymer we use. Okay, and if you continue the heat treatment up to 1800 degrees C, you form stoichiometric silicon carbide at the temperature of 1400 degrees C. So we were able to print such a carbon-rich PCS that it composed of silicon carbide powders and silicon powders. Okay, then the pyrolysis at 1000 degrees C are done under argon with a very low volume sheet cage, and then at 1400 degrees C to produce stoichiometric silicon carbide through the reaction of silicon powders with the free carbon that is produced from the carbon-rich PCS. Let's go to the characterization of this product. So we have still improvement to do, and this is under investigation. Especially, you can see, despite the fact that the texture is seems to be quite dense on the image, by Archimedes method, we measure a relative density which is quite low, 71%, as you can see here. This is mainly due to the development of open porosity, and as I mentioned previously, we did this 3D printing in air. Therefore, we introduce oxygen during the 3D printing in our polymer, and this oxygen is kept in the structure of the final materials, and especially it is removed at high temperature, and it develops the porosity of our materials. Therefore, you have a large part of open porosity, which decreases the relative density of our materials. And because of this quite low relative density, the mechanical properties of such materials are not quite high. I mean, compared to dense silicon carbide, but if you have a look on silicon carbide which are produced by 3D printing, we are in the range of the mechanical properties. I mean, in terms of Young modulus and flexural strength, we are in the range of the materials which are produced by 3D printing, especially maybe, and in particular in the top range of these materials. So now let's move to the conclusion, and we have a lot of perspective related to this work. So I hope I convince you with the interest to prepare stoichiometric silicon carbide as a three-dimensional part using a carbon-rich polycarbonylene mixed with silicon carbide powders and silicon powders, and then the mixture has been thermalized at 120 degrees C to link the polymer chains to the powders and to increase the gas transition temperature of the polymer, avoiding the collapse of the piece that at the exit of the nozzle. So we can produce a large part of pieces, as you can see here, more or less complex. We can also produce lattice structure, you can show after. And this process is quite flexible because you can change the nature of the powders that are put in your polymer. For instance, you can replace silicon carbide powders by titanium carbide powders, and you can prepare at the end of your process composite. I mean, titanium carbide dispersed in a silicon carbide matrix. You can also replace the silicon powders by boron powders. In that case, you don't form stoichiometric silicon carbide, but you form a boron carbide silicon carbide composite made of boron carbide powders dispersed in a silicon carbide matrix. So we have a PhD who is working on this topic, and we have several actions dedicated to such materials. Especially, we are trying to optimize the polymerization degree of the polymer. I mean, we need to control or to adjust the thermolysis temperature from 120 to 160 degrees C to reach an optimal viscosity as a melt and produce defect-free pieces at the exit of the nozzle, because sometimes you can observe some pores just after the extrusion, mostly because the extrusion temperature is not well controlled. We are doing structural, chemical, and rheological characterization of such materials, and we are in particular investigating the extrusion process in a glove box under argon, and we immediately observe a strong decrease of the open porosity in the final materials. If you remember, we got an open porosity of close to 23% when we performed this 3D printing process in air. And since we introduced this 3D printing in the glove box under argon, we were able to reduce this open porosity to 14%. So we have still progress to do, but it's a good step to increase the mechanical properties of these materials, which are also under investigation. So as I mentioned, we have a lot of to do regarding this topic, and it is quite flexible because you can, in fact, prepare a large range of composition using this process if you can prepare thermoplastic preceramic polymers. So you need to work with the chemistry of such preceramic polymers, and if you succeed in the synthesis of thermoplastic polymers, you can imagine to 3D print such polymers in order to prepare 3D parts in carbide, nitride system, but also as ultra-high temperature ceramics. And since recently we are working on fibers reinforced ceramic matrix composite, so we just bought this machine that consists to pass fibers, carbon fibers, through our polymer as a melt, and to extrude at the exit of the nozzle our polymer, which is reinforced by fibers, and in that case you can prepare three-dimensional parts as fibers reinforced ceramic matrix composite with a silicon carbide matrix. So such materials are seems to display great potential in terms of mechanical properties, especially from industrial partners that look for such materials, that will look for such materials in the future. Some announcements. So there is a special issues in this new journal proposed by Nature on additive manufacturing of ceramics for extreme environments. So the deadline should be in July, and with especially Professor Paolo Colombo, you know him probably, we are editing this special issue. So if you are working on 3D printing of ceramics, especially for extreme environments, so don't hesitate to submit your paper in such an issue. And regarding polymer-derived ceramics, we will organize next May 2025 symposium dedicated to polymer-derived ceramics, especially with Professor Ravi Kumar and Dr. Günther Motz. And so if you are working on this topic, polymer-derived ceramics, this is a symposium S4. If I remember well, the deadline to submit the abstract should be mid of December. So please don't hesitate to submit your abstract for this very nice conference that will be held in Vancouver, in Canada, next May. And at the end, I would like to thank you for your kind attention, and I would like to thank all my team and also our sponsor that financially support our research. Thank you very much.
Thank you, Samuel, for this nice talk, which is open for discussion. Is there any questions? Yes.
Process when you do in air, what's the amount of SiO2, silicon oxide.
This is clearly the problem. You can see if you have a look on this composition after pyrolysis at 1,000 degrees C, we have a quite high oxygen content. So I could not give you exactly the proportion of silica, but we have, for sure. And since we did this 3D printing under argon, this is significantly reduced. Yeah, but I should also mention that this polymer is a commercially available polymer, and it displays oxygen, at least for 8%.
So there is one more question.
Very interesting work. You mentioned that you have used both piston type and screw type process.
We use Sirang.
Yeah, yeah.
Sirang.
Pardon me?
Sirang we use,
Okay, yeah.
not to screw.
Now,
We
do
use.
you think that there will be any change in the shear thinning behavior? Because why I'm asking is, in case screw type also can give similar results, it can be useful for the continuous extrusion, continuous process.
This is clear. There will be clearly a difference between a screw type extrusion and a Sirang. I don't have any experience in a screw type extrusion, but at least the shear rate will be different. This is clear. Yeah, this is clear.
Yeah, nice presentation. Can we go close to the percolation threshold, like filler fraction? Because
You mean?
percolation threshold, like what would be the filler fraction which can put it in the polymer?
I mean, just based on the elemental composition of our polymer, so we were able to measure the carbon content. So we add the appropriate amount of silicon powders, which is close to 13 volume%.
Okay.
And then we continue because the viscosity was still low as a melt, and therefore we added silicon carbide powders with a diameter around 1 microns to increase the viscosity to a range of 10,000 Pascal per second as a melt.
Okay, so we cannot process like Teflon and other things which has a very high melt viscosity, right?
Yeah.
Second question is that silicon carbide exists in different polymorphs. You have sintered it at 1800 or heated it at 1800. What would be the crystal structure at that temperature? This one.
You mean?
Yeah, 1800.
Yeah, this is beta silicon carbide.
Beta,
Yeah.
right? Okay.
Yeah.
Okay, thank you.
Yeah.
So we have one question in the back.
If we use SMP10, we will get stoichiometric silicon carbide, right?
No.
Okay.
You have at least, I would say 15 weight% of carbon in excess in the polymer, if I am right. And at the end of your process, you will get carbon containing silicon carbide. Yeah. I mean, the color of your piece will be like this, black. Like this, if you use SMP10. And SMP10 is not a thermoplastic polymer, it is a liquid one. And there is a lot of work in US in particular to transform this liquid polymer into a thermoplastic polymer, especially by NASA, and they don't succeed a lot.
Thank you.
So one last question.
Yeah, so in that figure, SiOC, I mean, O0.1 you are getting. So is it something very close to silicon oxycarbide, so which will actually improve the oxidation resistance?
After pyrolysis at 1,000
this
degrees C, indeed we have a silicon oxycarbide matrix. This is clear. But after 1,400 degrees C, we don't have any more oxygen. It is released.
Yeah, 0.1 is shown.
Yeah, below 0.1 because
Okay. Yeah. Right. Thank you.
Okay, we can close. If you have further questions, don't hesitate to contact Dr. Bernard in the high tea break. Thank you again, Samuel, for your talk. And don't go away. We have a memento. and we will hear the talk of Dr. Parag Bhagava. He's from IIT Bombay in India, and he will give us some insights related to the 3D printing of ceramics through photopolymerization processes. Dr. Bhagava, the stage is yours. Please go ahead with your talk.
Good morning, everybody. It's a pleasure to be here, and well, I've enjoyed the first talk from Dr. Bernard. My talk is different, as you can see. It's on slurry-based, photopolymerizable suspensions. All right, yeah, thank you. So this is, I mean, the generic term for these kind of processes is wet photopolymerization, but you will see as I go through the talk, we've used two different kinds of machines. Our work is not so much on the machines, but more on the material side of it. This is mostly work that I'm presenting is my doctoral student, Seema Negi. She's just submitted her thesis. And Professor Prasanna Gandhi, he's a collaborator in the mechanical engineering department at our institute. So very quickly, I can, go faster on this. Of course, these things don't need any further elaboration. All of you who have already seen the first presentation also have a feel, except that, as I said, this is more slurry-based. And these are the steps, right, that we typically go through any 3D printing kind of processes. Only thing here, just to quickly point out, if some of you have been following this field, stereolithography initially came up where materials were very similar, but the build times or build rates are much slower because, in the stereolithography method, you know that we use a laser and it works in a scanning mode, right? And from that, so to say, and the thought that, how other printing methods work in conventional industry, these ideas on digital light processing have evolved. And that's how, these machines have come up. But you can have two different sort of modes of printing. Either you can have a top-down or a bottom-up kind of, configuration in terms of printing the part. Whatever I am presenting is mostly bottom-up. And that is because of the way machines are, right? So the light exposure is from the bottom. The only thing, if you are wondering why is it at all important, I think there are certain reasons why machine builders have come up with this bottom-up approach. But there is one constraint which we have seen, at least practically, when we were doing parts, printing parts in our lab, is that because in the bottom-up approach, you can see that logo sort of IITB, which is representing the part that is getting printed on the platform. There has to be an adhesive layer, right? So it's sticking onto that, and that adhesive layer must support the weight of the part that is getting printed. So to some extent, the size of the part or the weight of the part that you can build in this technique can get limited, right? That we saw practically. In the other one, that's not an issue at all, right? I'll talk about this DMD part a little later, what you see. Yeah, so this is just to give you, again, very introductory or very, elementary things here. As I said, the materials that I'm going to talk about are all, they are using photopolymerizable resins into which we disperse our ceramic powders, right? So very, typically when we do any ceramic processing which is slurry based, we look at dispersion, put it in a medium. Here the medium is a resin, which is photocurable, right? And the only thing that, which is important, which presents challenges for these techniques are, as you can see, and as you build more complex parts here, the slurry, uncured slurry, so it's not that, you have, of course, there is some volume of slurry which will be uncured, right, depending on the design that you make. And the more complex the parts become, the more challenging it becomes to remove that uncured slurry, from within the part. So this is not highlighted a lot in the literature, but this is extremely important, as you go further with this technique. The second thing is, compared to when people are used to, for example, injection molded parts, for example, right? Or if you are working with thermoplastic binders, the way debinding is happening there is very different. Here, this undergoes cross-linking. So remember that debinding part is going to be very different, and I personally think it's even more challenging to debind these parts, right? Particularly in terms of the heating rates that you have to use. That is going to come up later in my talk. And when we started our work, we had actually, this happened for various reasons. When we started our work, we didn't really have the machine later on which we ordered, and I think there's a talk by Lithos here. We got that machine later on, but initially, just to get going, we started using this machine. This is actually a resin printer. So it's not a ceramic 3D printing machine. It costs about 20,000 Indian rupees. And I'll just show you a few slides. Why I put it up here is I think it's very useful in terms of, sometimes you have resource constraints, but you still want to work on materials, right? Materials development. So you can use a 20,000 rupee machine to explore these materials, right? And to look at 3D printing, and then that, then allows almost any institution to kind of, look at 3D printing at least. So this was a resin printer, as you can see, and the steps of what we do. Essentially similar thing as you do for resin printing, except we introduced our own slurries. And there is no automation. So all your spreading of the slurry is going to be done manually, right? But otherwise, it's, light sources at the bottom, as I said. This is, on the right side, you can see the actual picture of the Lithos machine, which we got later on, which is also referred to as lithographic-based ceramic manufacturing. In this case, there is automation, as I said, compared to the previous one. So you still have a vat, you still have the light source at the bottom, and you have a wiper blade, which allows you to spread the slurry so that you can get a uniform layer thickness, right? Maybe somewhere from 25 micron and upward. So each time that you go through, you spread a layer, you allow exposure from the bottom, and the platform sort of lifts up, and then again you have the slurry introduced, and the wiper blade spreads, and that goes on, right? And that's how you build the part. These are not our parts, but these are, pictures available from literature. You can do reasonable complexity here with these kind of machines. Now, these are, it's maybe worth spending 1 or 2 minutes for those at least who are not very familiar with this entire idea. So, of course, powder is there. And as I said, dispersion is a key. So, if you work with different materials, you have to look at dispersion part. How do you disperse these materials? And the choice of the monomers. So, in terms of materials development, what material resins are you going to choose is going to make a big difference, including in terms of viscosity, including in terms of how do you debind, and those kind of things. And definitely there has to be a photoinitiator, because this is getting cured by exposure to light. In terms of the characteristics of the suspension, penetration of light is extremely important, right? So we have a lot of discussion or analysis of cure depth. The refractive index plays a big role here, So if there is a greater mismatch in refractive index, your depth of penetration actually gets limited by that. Of course, if you are working with materials which are very high density, right, in case, the extremes could be, something, let's say tungsten carbide just in case, and particle size, all of them can also result in sedimentation. So that needs to be looked at, right, when you are sort of formulating your suspensions. Cross-linking ideally must happen in short span of time, otherwise, again, it will reflect on your build time. Shear thinning is absolutely necessary to get a uniform layer by spreading, as I said, you have a wiper blade. The energy for the curing is important in terms of, again, what kind of energy input that you have to provide during curing. And ideally, if you can have as high an extent of curing, right? And finally, this is also important, I didn't mention it, but you can imagine in the machine that I showed, the slurry spread, or it's in the vat, it's spread, and it's exposed from the bottom. So there is a challenge that your cured material should not stick to the surface from where the light is exposed. So there is a mechanism in the machine where it tilts it and allows it to, separate it, and that's how it gets lifted. Otherwise that becomes a challenge. So the bonding to the vat should not be, very strong. This is just to illustrate very quickly this idea which I said earlier, particularly about the refractive index. If you can note here that on the left, the table on the top left is typical, resin systems. And you can see the refractive index in the range of close to 1.5. And on the right side, if you see the ceramics, if you see one of them which comes very close is silica, may not be the most important material, let's say. But when you have such close refractive indices, you can see at the bottom in red, you can get very high cure depths. But when you have mismatches, increasing mismatches, your cure depth, it reflects immediately into the cure depth, right? So that is an important issue to sort of at least keeping it in mind. Second thing, which is not entirely highlighted here, is because of these differences in refractive index, you also get a lot of scattering. So your cure width increases, okay? And that's why you lose resolution. Even if you had, if it was not limited from your machine, because of these refractive index mismatches and the scattering, you get, larger cure widths, right? So your resolution is lost. This slide is primarily, the popular, let's say, dispersing agents, oleic acid, stearic acid are very common with these systems. But it's just reflecting here that oleic acid is far more effective to work as a surfactant for these systems when you want to disperse in resins. And on the table on the right just illustrates the idea, like typically in any suspension, you have to figure out the right amount that you add to achieve the minimum viscosity. Of course, contact angle also reflects, how well it gets wetted and how do you make that stable suspension. This is again illustrating the same idea in 2-3 different ways, because oleic acid has a better, stearic acid has a better solubility parameter with respect to these solvents. That is illustrated in this schematic. And on the right side, you can see if a dispersant is more effective, it will give you narrower particle size distribution. So it gets validated there, right? Now this is about, as I said, we used a low cost, this is like a 20,000 rupees machine, which we used for different materials. And I'll just show you, we did some work on alumina, hydroxyapatite, and some also composites. So these are list of materials. You can notice here, acrylates are the most common, very popular. You have a photoinitiator there, and among surfactant, as I said, oleic acid is one popular one, but there are many other options here. These are the exact, percentages, for example, which were utilized with the ceramic powders, about 45 volume % solid loading, but don't take it literally, in the sense that there are also ways to keep improving this solid loading, and that is one of the goals many times in these kind of work. In terms of the steps, it's very critical, just want to mention that very quickly, that we do a dispersion or a coating with the surfactant as a separate step. So we don't do it in a single step. So we coat the dispersant molecules on the powder in a separate step, extract that, right, get rid of the solvent, and then put it back into the resin, right? And that's how we go towards making these slurries. And these are, illustrating some of the ideas that I mentioned earlier. But we always, whenever we work with a new system, we always like to look at the cure depth that we are able to achieve with, for example, exposure time. I have not put all the data. Also, we would want to look at cure depth as a function of solid content, for example, right? So it's going to be affected by a large number of parameters, this cure depth. And that makes a difference in terms of when you make a choice of the layer thickness during 3D printing. Of course, your layer thickness, your cure depth must exceed certainly must exceed the layer thickness that you're going to choose, right? That is how interlayer bonding is going to happen. You can't do the other way around. And you can see the effect of here exposure times. If you increase the exposure time, this red lines that I have drawn for the part that is, or the substrate that is shown there, with increasing exposure time, you actually, you see, because of the scattering, you are going beyond what is the geometry that you need. And similarly, this geometry with a hole there, if you have higher exposure time, you literally, during printing, you are closing the hole, you are losing that geometry, right? So these are problems which occur because of the scattering. This is the microstructure and one of the, demo sort of shapes made by that low-cost printer. And you can see, microstructure doesn't look very different from what you would get otherwise conventionally. You do have some residual porosity, but otherwise it looks, and the shrinkages are visible there. The solid content here was much lower than what you would want to build. So you can see there is higher shrinkage, higher than what you typically would see in, let's say, slip casting or powder compaction. Right? This is some data from hydroxyapatite. This powder came from Ceramet, Sabyasachi, I don't know if he's here. But we utilized that powder and looked at two different surfactants. Oleic acid still gives you much better results in terms of dispersion here. And this is one model part that we built with the same machine, the manual spreading and all that. But you can still print quite well, right, with these slurries. Now, this is the part which I wanted to also talk about a little bit. This is the other machine, which is from Lithos, the lithographic ceramic manufacturing. And as I said earlier, that here the slurry spreading is all automated. And typically we use 25 micron kind of layer thickness, and you can see the energy exposure. You can go up to, let's say, 130 joules per centimeter square. We've looked at, also have some data with lower energy exposure as well. Yeah, I wanted to say that earlier, the heart of this technology, or this machine rather, is something called digital micromirror device, and I think this is one of the things that these machines are very expensive. But at the same time, this also allows us to get very high resolution, when you print parts from these photocurable suspensions. And these are, micro mirrors, and you can actually see that it can, in a single exposure, right? Unlike in stereolithography, you expose one layer at a time. So it's the manipulation of these micro mirrors, right? And literally individually, which allows you to get that resolution into the layer, as you are trying to build those features, right? Now, this is some data. As I said, we always look at cure depth to begin with whenever we work with different materials, and for example, in this case, a machine. This is for alumina slurries, and you can see the top left graph, which talks about different power, right, exposure, and also the exposure time. So cure depth is, of course, expected to change, right, with increasing power, you can see, and also with the exposure time. And on the right side, you see the similar idea, as I said earlier. Because of the scattering, you actually are getting curing beyond what you really desire, right? Your desired feature is only as indicated by that red line. On the bottom also, you can see with increasing exposure time, the similar kind of effect that I pointed out. And this is, again, illustrating now, for example, look at on the bottom where it's a blue colored picture there. So we had put in a single part intentionally, some, let's say, feature and the size as well, and you see that how you start to lose the definition of those features as you, go up with higher energy densities. So in this particular machine and this particular process, one has to really be watchful of that, right? To be able to retain the resolution of the features, right? On the right side, if you see, the part printed is actually almost, getting cured beyond what you desire, as I have mentioned earlier. So energy density is also very critical. Of course, it is also affected by the refractive index mismatches, as I said earlier. This is another challenge which we used to encounter when we began this work. For us, this was with this PhD student, this was our initiation into this particular technique. So it's very important, as I said, it's bottom-up printing. So each time, you have to ensure that your layer adheres to the platform. So there is a separate step in where you actually expose the material first for a sufficient time, which is not really part of your component, but that helps to bond it to the build platform, right? So the middle image and the right image both show problems encountered if you don't have proper curing, that you can actually get delamination from the build platform, right? And same way if the next layer also doesn't do well. So initially it's very important so that you don't have those kind of issues as you build these parts, right? So this particular part, when we were printing, we had encountered this problem, but then we could take care of it, as I said, by that you have to actually adjust those parameters so that you make sure that you're bonding to the platform as well. So this is one for example, and the picture here, the bigger picture here on the bottom, you can see is how it looks like when it's printed and, now on the build platform, right? That's how it gets built, and then you have to separate it out. This is just showing shrinkages. Yeah, this is one kind of, just to test out the capabilities of machine, and we had the hydroxyapatite slurry, so you could print this part with complexity, which is anyway expected from these machines. Sintering shrinkages in the range of 28 to 30%. With alumina, you can get lower shrinkages. This is with hydroxyapatite, you get much higher shrinkages. And now here showing some influence of, as I said, these are cross-linked systems, right? So the heating rate plays a very big part. And to me, that was initially, I was used to working more with thermoplastic systems, where debinding is far easier. But if you can see here, in this case, the effect of the heating rate, the leftmost picture shows you, I don't know whether you can see it back there, but you can see cracks there. But look at the heating rate, right? Less than half a degree C per minute was required before you could actually get crack-free parts, right? Also, the other thing is that there is a lot of research now going on. We have not yet undertaken so much work, but people are looking at use of additives which could be added in the slurries, which ease out the binder removal at a later stage, right? So in this case, for example, PEG 400, which is also very commonly used as a plasticizer in conventional ceramic processing was used, and that also helps to improve this part about, not getting cracks because of the, its ability to accommodate the stresses, right? This is almost towards the end of my talk, but this is one thing which we examined using this machine, and we thought that let's pick up something which also helps to understand, whether it can do, for example, something which can be done, let's say, by tape casting. But here, this is more like, it's not, it's into fraction of a millimeter, right? We were wanting to make, let's say, 300, 400 micron thick parts and wanted to see what challenges we'll encounter. So we picked that up intentionally. And what we saw, as you've seen the pictures at the bottom, that when you try to make thin parts here, right? And remember that the cure depth will be, generally speaking, in terms of, let's say, 100, 150 micron, right? So what happens, what we observed here is, in trying to make a thin part, the layers which get printed early on get multiple exposures, right? And as it gets multiple exposures, right, yeah, so it builds in some residual stress, okay, because of the differences in extent of curing, and that is visible from what we did in terms of nano indentation. If you see here, in terms of nano indentation, there is a clear difference between what you see for the first layer, which is the repeated, which would have got the repeated exposure, right? So the extent of curing as compared to what you get in the final layer, right? So this can probably be a challenge in building other parts. For us, it was more of a demonstrator, right? So nano indentation clearly brings that out. Of course, you can prove it by other means also. You can run you can run samples with intentional differences in exposure and do a maybe thermal analysis, for example, right? So on the right schematic just shows why you expect a warpage. The rightmost part, the real printed part, the rightmost part, so what we did was, to account for this, we eventually, after printing, exposed the part to the similar light source, but for a longer time, so that we make it more uniform, and then you are able to reduce the warpage. So this is some kind of a limitation, for example, could be expected if you are building parts which are much, much thinner. This is one, just kind of think of it as a case study, although part doesn't look very complicated, but it was interesting to see what challenges we are facing. So there was a company which approached us, which wanted to just do some coupons, basically for testing the capability of this technology, and later on they want to build some more complex parts on this. But just to even build these kind of coupons, it was actually challenging, but I should say also this was our first experiences. So I'm not trying to say that the technology or the machine is a limit, but this was a very interesting learning experience. We just built them in the orientation that they are shown here. But if we change the orientation and allowed the exposure, each exposure, the layer sort of cross-section width was lesser, that actually ended up solving the problem. So when we build these parts, okay, at a certain orientation with, of course, supports, Now the interlayer bonding was no problem. You did not have any issues in terms of cracking, and this could be, as you see at the bottom, the final sintered part was completely defect free. So I think that is all I wanted to present. Whatever I mentioned is kind of sort of summarized here. But as I said, just to give you only few words of summary in terms of at least this DLP technology, the choice of resins is extremely important, and I think there will be lot more work we will see in the future in terms of if we can make it, if we can facilitate easier debinding, like I said, including use of additives, for example, right? So that is one thing that is going to, remain a constant, I think, sort of in terms of directions of research. The other thing, which seems trivial to begin with when you get into this technology, but to remove uncured slurry from the parts, particularly when you have complex parts, maybe you have internal channels and things like that. How do you remove the uncured slurry? So there's a lot of interest in terms of, maybe for example, if the industry has to get into and utilize some of this technology, that also needs to be established. Of course, the last thing I just want to repeat that part, for me it was initially a surprise that in terms of, when you think of thermoplastic binders, you can do catalytic debinding, for example. So maybe that kind of things have to be looked at. We have not looked at. Right? So to basically similar route as it was done in thermoplastic debinding, that how do you shrink the debinding time? Right now, because we do conventional, we go extremely slow heating rates, it works, you can get refractory parts. But I think that is also another area here as well, which will need a lot more attention. So I'll stop here.
Thank you. Thank you for your talk. So is there any questions for Professor Bagava? So we are behind the schedule, but still we can take a question.
What is the limitation of thickness? Is it a limitation of thickness of the photo? This thing?
See, what is happening is if you build features, let's say if you build very fine channels within it, right? To remove the uncured slurry, I have to use call it a solvent for lack of better word, but you need that solvent must get into those channels and help to remove the uncured slurry, right? So that at times becomes a challenge, and then it should not also happen that solvent somehow starts to affect the features that you printed, because if there is slight uncured slurry within the printed feature, it will start introducing defects, right? So that's why I said that it's important to cure it well, but at the same time remove these uncured slurries.
Thank you.
Yeah.
So one
sure.
last question. Yeah.
Can you make full parts, because dentists require them and India is a huge market. We still use a lot of imported hydroxyapatite.
Yeah. See, any dental things, I would say, of course, there may be other commercial reasons, maybe separate, but these machines are excellent at printing the scale that we need for dental materials. They are excellent. And then, of course, in a single print, because of the size, you can do large numbers. So I think in the long run, these kind of technologies would, because the resolutions are quite high here, right? So people are looking at, let's say, what is called fused filament fabrication. It's extrusion based, and ceramic loaded filaments, you lose the resolution there. But for dental parts, otherwise with high resolution, right, and in a single exposure, you can build fast, and for small parts, it's great. So as long as commercial, if it makes commercial sense, I think people will go for it. Yeah. For hydroxyapatite, you mean? So mostly, just for hydroxyapatite, I'll say, most dental crowns I'm saying, or, the main structural part is not done with hydroxyapatite, right? Hydroxyapatite may come in for other things, maybe bone fillers and all, right? But otherwise, you can print alumina, zirconias, and all those things very easily here. Yeah.
Thank you once again, Professor Bagava.
Thank you very much, Dr. Emmanuel, for conducting this session. We are 10 minutes behind the schedule, but I think it has only eaten away the coffee time. So please head for coffee in the main dining hall. And the next session will start at 11 o'clock here. The additive manufacturing session will continue here at 11. And all other parallel sessions will continue at 11 o'clock in different halls. I think one of the halls is flooded is what I'm told, but let me just come back to you if there's any update on that. But otherwise, this additive manufacturing session will continue here. So please have your coffee and come back at 11. We still have 20 minutes. Thank you, Emmanuel. Emmanuel, can you do this?
3D printing obviously is not like with polymers or metals that you get the final part out of this 3D printer, but it's a two-stage process where you first print the green part and afterwards do the binding and sintering in order to end up with the final component. And as we already heard from previous speakers, very often this debinding and sintering is more of a challenge than the actual 3D printing. About the 3D printing process itself, I always like to link it or to compare it to a visit to the dentist. When you get the white filling, the dentist puts a paste into the cavity of your tooth, he shines light onto it and solidifies the material. And the same very principle is also employed here in this technology, with the main difference being that we don't want to cure the whole material or the whole reservoir, but we want to cure only a selected area. And this is done by a selective exposure, mask exposure, as you can see here, or not. Sorry. Thank you. All right, sorry for the short interruption. Mask exposure, as you can see here, to transfer the whole layer information in a single step. And by doing this layer by layer, it's possible to fabricate quite intricate and complex designs. Afterwards, debinding and sintering, so you get rid of this photopolymer network at the lower temperature regime, the so-called debinding, and then at higher temperatures you fully densify or densify the material to a degree as you want. Of course, this elimination of the porosity during sintering is accompanied by a certain amount of shrinkage, as you can see here on this slide. So for alumina, for example, this is typically in the range of 20% linear shrinkage. But luckily, this is something that can be well compensated by just scaling up the part which needs to be 3D printed accordingly. So at the end of the day, we are able to get to the required precision. Here's a quick overview on different materials that we're working on a regular basis. The working horses obviously are structural ceramics, oxides like alumina, zirconia, ATZ, ZTA. Then we also moved into bioceramics, which now are basically the second big topic for us as a company, so making bone replacement materials, making materials for dentistry. And more recently, we also started to experiment and work with non-oxide materials, functional ceramics, silicon nitride, carbide, aluminum nitride, very interesting material I'll be digging a bit deeper into in a few slides, and also piezo ceramics, the PCT, lead-free variations, and so on and so forth. So very interesting topic I always like to mention is this simulated lunar regolith. This is coming from collaborations with the European Space Agency and NASA, where it's about using the material abundant on the moon or the Mars in order to use that for 3D printing there, so at space stations or moon bases in the more or less far-fetched future, but it's at least a very interesting topic to work on. And we are one of three technologies, 3D printing technologies identified by the European Space Agency to move into a second phase for the exploration of using additive manufacturing for in situ resource utilization. Because we also heard with the previous speech how difficult it is to make intricate objects, especially small channels. I also wanted to highlight this design here. It's definitely something which is not straightforward. 3D printing of ceramics especially, it's not plug and play. This is definitely something where you also have to undergo a learning curve, and you really have to go deep into parametrization. So making a structure like this requires different parameters than making a bulky objects. But if you design the process in the right way, it's really possible to achieve resolutions in the double-digit micron range. As you can see here, struts of 50 microns, channels of around 100 microns. So in principle, it's possible to really go into extremely highly resolved parts. And this is also at the moment the biggest business case. Our main customer, which is located in the US, is currently operating more than 20 printers, working in shifts, and in 2023 he was producing 3.5 million parts. So this is definitely not prototyping anymore, this is fully fledged series production. In 2024 it will be 4 to 4.5 million parts most likely. So this is definitely a success story where 3D printing of ceramics really has been uptaken in the industry. And here, that's also maybe interesting to highlight, the required tolerances for the main feature of this part are 10 microns. So we really have to achieve extremely high precision using this technology. All right, moving on to non-oxide ceramics, especially in the context of this conference with sustainability. Non-oxide ceramics can play a pivotal role in order to enabling some of these novel technologies. Silicon nitride is the material I want to start presenting. Here we are more precisely using a so-called Cylon, so a silicon nitride that is containing 5 to 10% of a glass phase to make the sintering easier. Pressureless sintering is feasible, also sintering at lower temperatures, which of course also leads to some savings in energy. And important was to be able to demonstrate that we can achieve the same basic mechanical properties as in a conventional manufacturing technique. So we compared or benchmarked ourselves towards isopressed Cylons, and we were able to really get to the same microstructure as shown here. So full densification, of course, also aided by this gas phase. Completely homogeneous microstructure, completely isotropic, which is also very important. 3D printing being a layer-wise technology, we need to avoid any artifacts from this layer-wise buildup in order to have really fully functional parts. And if you look at the final properties, you can see in terms of strength, in terms of hardness, in terms of thermal properties, it's really completely on par with conventional manufacturing technologies. All right. Moving forward, aluminum nitride may be an even more exciting material if you're thinking about the big challenges ahead in terms of power electronics, e-mobility, because this ceramic has, as you all know, a very nice property being, on the one hand, electrically insulating, but also exhibiting a high thermal conductivity. On top of that, it has a CT very close to that of silicon, making it really an interesting material. For example, a substrate heatsink for, as I said, power electronics or batteries, e-mobility, and so on and so forth. So this is definitely a material that can be a bit of a game changer, and especially if we're thinking about heat management, specific surface area complex designs are very important. So obviously 3D printing can be something that is can be a big aid here, but 3D printing is not enough if the properties are not there. So first we looked obviously into the basics. So can we fully densify the aluminum nitride? Can we get rid of these layer boundaries during densification? As you can see here, yes. So if we compare it again to cold isostatic pressing, you can see that the basic microstructure that was obtained is on eye level. No artifacts from the layer-wise buildup visible in the sintered microstructure. So the baseline is looking good. And then, of course, we also looked what can we achieve in terms of designs. And here, as you can see here with this heat exchanger design, basically the creativity is maybe not endless, but it definitely gives you a lot more freedom than with conventional techniques. So also looking at the other specs, thermal conductivity, which as I said, is the main feature of this material, 210 watt per meter Kelvin. Also very decent bending strength, which is definitely in the ballpark of aluminum nitride ceramics. So all in all, this is definitely a material where I'm 100% sure that this will be playing a big part in the future, not only for us as a company, but I think this will also be catalyzing developments in different industries in the future. And also in this context, we're having a very interesting European collaboration at the moment going on, a project called AIDA Innova, which is in the phase of being wrapped up. This is also involving, for example, the CERN in Geneva, Switzerland, so the Large Hadron Collider. And here we are actually 3D printing the cold plates, so basically the heat sinks for the detectors for the next generation of the Large Hadron Collider. So basically here you can see the design. It's a flat top, and on the bottom side you have these cooling channels, which why it's necessary to employ 3D printing. Moving on to another material that was already introduced in this morning mainly by Samuel Bernard, silicon carbide. Because of its optical properties, this is definitely one of the toughest nuts to crack for 3D printing in general, and especially for photopolymerization-based technologies. So we have tried out a similar approach to silicon nitride, also using a glass phase, so the so-called liquid phase sintered silicon carbide, sintering at quite high temperatures. Still, as you can see, the densification should be better, which is why we also looked a bit to the left, to the right, for example, into silicon infiltration, so reactive bonded silicon carbide, where you print basically silicon carbide green part, you do pyrolysis. So from the binder, you create residual carbon, and then upon infiltration with liquid silicon, you can form a second phase of SiC, making this also a quite interesting approach. This particular part here on the left-hand side, we also have on the booth outside, so you can also have a look for yourself on this particular design. So this is also a quite interesting approach, and because it was already introduced in the morning, of course, also polymer-derived ceramics or pre-ceramic polymers are a possible vehicle to achieve this kind of material class. Here we already started working quite early, as you can see, almost 10 years ago, some collaboration with Paolo Colombo from Padova. I would say decent first results. You can see that the achievable wall thickness was extremely low due to the large shrinkage and the low ceramic yield. So in subsequent times, we also tried to kind of combine the two approaches I presented earlier, the suspension-based approach and this pre-ceramic route. So we introduced SiC fillers into the pre-ceramic polymer in a collaboration with the Technical University of Vienna, with Thomas Konecker. And we were able to improve the performance. So linear shrinkage, or shrinkage in general, went down, ceramic yield went up, and we actually came already to quite decent performance in terms of characteristic strengths, for example, 325 megapascals, and also a viable modulus, which is not too shabby, but of course not great as well. But definitely something that will be explored in the future in order to maybe even further increase this concept and the performance of the parts. You can still see here it's not completely isotropic due to the layer-wise buildup and the comparably larger particles of silicon carbide we had to use. You can see that there is still some sort of texturing in the part, and this is topic of ongoing research to be improved in the future, hopefully. A very interesting concept was also to kind of translate this idea of, in this time not using SiC as a filler, but using organometallic additives in order to be able to create PDCs with an inherent catalytic activity. So again, this was a collaboration with Theo Wien and Thomas Konecker, where we tried the introduction of different metals using organometallic compounds. And on top of that, we tried to introduce a photopolymerization initiated phase separation. to increase the porosity level, to increase the specific surface area, and by doing so, of course, being able to have a larger surface, a larger catalytically active area. And this was actually also quite successful. So here you can see the resulting parts after printing, after pyrolysis, and yeah. We also looked then into the catalytic performance. So you can see here that we were focusing mostly on the nickel type of the basically treated SiC. In the beginning, the results weren't great after pyrolysis, so we did some post-oxidation because the assumption was that because of some residual carbon, the catalytically active centers were not accessible, and this could then actually be demonstrated that doing a post-oxidation at 400 degrees C, the catalytic performance could be significantly increased, as you can see here on the graphs on the lower right-hand side. So we're able to achieve 100% selectivity for this CO2 methanation reaction that was catalyzed, and also a quite decent and promising conversion rate. So this is definitely also a quite interesting area that can be propelled using additive manufacturing in the future. Of course, these slides on silicon carbide also led me to do some sort of short digression, because I think what's also important to highlight here that maybe with additive manufacturing, it's not the case that one size fits all, meaning that not every material, not every application will be best targeted by the same manufacturing technology. And I think silicon carbide, having this very high light absorption, is a very good example of a material where maybe alternative technologies are more easier way forward, which is why we are also exploring other technologies at the moment, as this laser-based slip casting approach, laser-induced slip casting, where we are using the thermal energy of light in order to do a drying process, which of course also enables us to easily structure darker materials, UHDCs, silicon carbide, of course. Here you can see some examples. Of course, there's not only upsides. As you can see here, resolution is not great, so this is more of a near-net chip technology where you still have to do some post-processing, some machining in order to get to the required surface finish and resolution. But overall, you can achieve quite massive components, and also density is good. The strength is quite nice, 300 plus megapascals. So it's definitely an interesting way forward for this particular class of ceramics. Something new that we are currently playing around with in the R&D lab is this layer-wise slurry deposition process. Here we are trying to combine slurries with inkjet manufacturing, and the background is because of the slurry, we can increase the green density, and using inkjet deposition, we can also enable the manufacturing of darker materials. So this is again an interesting approach for making, for example, silicon carbides, but maybe also a gateway into the manufacturing or the 3D printing of CMC type materials. And with this, I'm coming to the last section I wanted to highlight, because this is also a quite hot topic on R&D scale at the moment, and this is multi-material printing. Here we are again back at the lithography-based ceramic manufacturing or wet photopolymerization. The basic principle is basically the same that I introduced in the beginning. We are using light in order to selectively cure a photocurable ceramic suspension. The main change is that we're introducing a second reservoir, so a second ceramic suspension. In principle, you can also use a third and a fourth but at the current maturity level, we are playing around with 2 materials simultaneously. The vats can swivel around below the building platform, and by doing so, the building platform or the parts can dip into one material and then in the second. Not only for alternating layers, but as shown here, it's also possible to combine 2 materials in each and every layer, making this extremely powerful when it comes to further increase the complexity of the printable designs. And here we are doing at the moment some first collaborations with a university in Vienna, the Montan University of Leoben, where we are looking into mainly exploiting residual stresses coming from using 2 slightly dissimilar ceramics. So as I said, we can 3D print together 2 different materials, but of course you also have to co-process them afterwards. So you have to co-debind them, you have to co-sinter them. And typically these ceramics have different sintering temperatures, they have different CTEs. So at the end of the day, when the part is sintered, you typically have some residual stresses at the interface between the 2 materials. And this is something, if you design the part in a smart way, that you can use to your advantage. For example, to increase the strength, as it's shown here, by using these laminate type structures of alumina and zirconia toughened alumina. By introducing compressive forces at the interface, we were able to increase the strengths from alumina, which is in this B3B, so the Bolson 3-ball test assessment, around 500 megapascals. The 80Z was at 850, 900. And using this laminate concept, we could increase the strengths eventually to more than 1 gigapascal, which is quite impressive for a 3D printed alumina-based ceramic. If you play around a bit with the design, you can also make a bit more complex laminates, and here we wanted to look into the thermal shock resistance. So we made this ABA type of structure, again using ZTA and alumina, and then we did some thermal shocking experiments. So we heated the parts up, we immersed them in water, and then we did some mechanical testing. And as you can see here at the figure, for this laminate type structure, it was possible to preserve the residual strengths to a much higher degree compared to the reference materials. So the reason for that is visible on the images in the center. So you can see that due to the residual stresses at this embedded layer, we had some crack arrest of the cracks introduced during thermal shocking. And this led to a significant better performance after thermal shocking compared to the monolithic reference parts. You can see this also, if you look here just at the crack pattern on top of the parts, here you can see the monolithic piece, and then you have this quite defined, homogeneous, almost repeated structure that you can see in the laminate structure. And of course, what's also important, you cannot only do this for laminates, which is why we also did the study here with this kind of turbine blade-like samples. You can also translate this concept, of course, to more complex designs. Because if you would only be interested in laminates, then you can do tape casting. You don't have to use 3D printing, obviously. And these designs were used to show that this is really possible also to translate to the third dimension. So you can see here on the right-hand side especially that the phenomenological behavior was exactly the same. And we again had this crack arrest at the embedded layer. And with this, I'm at the end of my presentation, and I'm happy to take any questions if there should be some on additive manufacturing of ceramics. Thank you.
Thank you, Dr. Schwentenwein, for this interesting talk. Is there any questions for Dr. Schwentenwein? So there in the back.
I don't need the mic. So with this multi-material printing, 2 parts. First, what is the XY resolution that you can get? And second, how do you prevent contamination when you go from one material to the other?
Yeah, very good point. So in principle, the resolution of the printers is typically 40 microns in Z direction. Depending on the viscosity of the materials, of the two slurries that we want to combine, we might have to not use individual pixels, but rather groups of pixels. So for the parts that we printed, we used 2 × 2 islands of pixels, so the resolution in the green state was 80 microns, so after sintering, keeping in mind the shrinkage, it was around 60 microns. And the contamination, a very good point. I did not show it here because this is more of a modular concept. So there's different cleaning stations, we call them, or cleaning modules that can be integrated into the printer. So after the material or the building platform was dipping into one material and it was exposed, it's cleaned, and then it only dips into the next material. So we can avoid cross-contamination. For a material class like here, ATZ and alumina, ZTA and alumina, cross-contamination is not super critical, so here we can use simpler cleaning concepts. For other types of combinations, I didn't show here, for example, our work on metals and ceramics. It's more critical because you can create short circuits, for example. So here a proper cleaning is absolutely crucial, and there you have to employ a different concept, which is why we are using this modular setup here.
One more question there.
What is the polymer you use for PDC printing?
For PDC printing, in the work shown here, we have been mainly using polysiloxane-based, so there's also the publications, I can share them with you, and we created physical networks. So this was not that we kind of end-capped these polysiloxanes, but we used the polysiloxane, combined them with an acrylate typically, and then we created an interpenetrating network. And by doing so, we of course had to kind of distort the correct ratio in order to end up being able to end up with proper SiC. But this enabled us to use this for lithographic printing because typically siloxanes are not inherently photoreactive.
How much percentage you could retain the polysiloxane in that mixture? Like you mixed it with another
This
polymer?
This depends on the co-monomer that you use. So up to 85% by weight, but density is pretty similar. It's not exactly similar, but in this ballpark, we were able to retain the polysiloxane content. We didn't spend a lot of effort on that. There's definitely room for improvement in this direction, but as we knew that we would have to make compromises here, we aimed for something in the range of 80–85% siloxane.
Some more question for Dr. Schwentenwein? This seems not to be the case. Thank you again, Martin, for your nice talk.
Thank you.
We go to the obligatory memento. So we move now to the next contribution, which is an invited lecture given by Professor Basavaraj Gurappa. He is from Indian Institute of Technology, Madras here, and will give a talk on processable Pickering emulsions for processing of porous ceramics. So, Professor Basavaraj, we are looking forward to your talk here.
Thanks.
Okay, good morning everyone. I just want to thank Ravi and all the organizing committee for this opportunity. And this talk is going to be about what is called as processable pickering, making ceramics by using a particular technique called processing of Pickering emulsions. And this work is done by Nitin, who just graduated, and he now works for BASF, and I work in close collaboration with Professor Manas Mukherjee, who is at the Department of Materials Engineering here at IIT Madras. And that's going to be the outline of my talk. I'll just briefly introduce what Pickering emulsions are, and then walk you through a few other things. Colloidal processing of ceramics is very well known. It's a technique where you start with either powder or a slurry of particles, and then you make gel, and you can remove the liquid by drying, and there's sintering and other things that are involved in the making of ceramic materials. And for today, what I'm going to do is to tell you a little bit about a case where we're going to replace. You should imagine that we're going to replace these colloidal particles or particles by droplets. Okay, and droplets in which these either oil or water droplets are stabilized by particles. Okay, that's the talk that I'm going to give today. And this concept of particle stabilized emulsions is not new. It's been there for a long time, and this is the work that dates back to more than a century. And this is the work of two professors by name Ramsden and Pickering, who kind of found that if you have two liquids, you can just like the way the conventional surfactants can stabilize emulsions, you can also use colloidal particles, silica, alumina, any of these colloidal materials, and you can make very highly stable emulsions. There's a lot of understanding of fundamentals of what kind of materials can form Pickering emulsions, and we kind of work on certain aspects of these materials, and that's how we kind of got interested in these materials. And I think the interest in Pickering emulsions is kind of is developing quite a bit. These are some examples of what people have been able to make. You can make porous metals, you can make open cell foams, closed cell foams, all by starting with Pickering emulsions as a starting material. And you can also make some really interesting structures. For example, you can make really nice hierarchically porous structures by using Pickering emulsions. Okay, that's one of the expertise that we have in the lab. And of course, in order to process Pickering emulsions, first thing you should understand is what are the strategies that work for Pickering emulsion formulation. Okay, that's been an area where there's a lot of work in the last 15, 20 years, and so I'm just going to walk you through a few strategies that are typically used. And I think making Pickering emulsions is essentially a simple process. You start with fluid 1, fluid 2, put in some particles, and you just mix them up, right? That's, it may sound very simple, but there's a lot of science behind making such Pickering emulsions. And it turns out that when you mix such a system, you can either get an oil in water emulsion or a water in oil emulsion. That is, we're thinking about oil droplets that are covered with particles or water droplets covered with particles, and there are many controlling parameters that kind of contribute to which type of emulsions form, and how does the droplet size depend on. And it depends on many of these parameters. For example, particle size is an important factor. Smaller the particle size are, smaller is the emulsion droplet that you get. Surface charge, I'm going to touch upon a little bit of that in the next slide. Surface charge is an important character. Wettability tells you something about whether you get an oil in water or water in oil emulsion. Typically, the understanding is that if you have a hydrophobic particle, they prefer to sit on the surface of water droplet, therefore you get a water in oil emulsion, and otherwise if it is a hydrophilic particle. And particle shape is an aspect that again has been kind of researched very heavily in the last 10 years or so, and of course oil to water ratio, because depending upon the oil water ratio you can have either water or oil as a minority phase, and typical understanding is that the minority phase typically gets emulsified. That means the minority phase is typically in the dispersed form, and the continuous phase is supposed to be in the the larger fluid is supposed to be in the continuous form. This is some examples from our lab wherein we kind of did some very simple experiments to understand the influence of surface charge on Pickering emulsion formulation. And these are experiments where what we were trying to do was to start emulsification with water and oil, and the particles were iron oxide particles, and they were dispersed in water. And it turns out that if you have, so the bottom two left images, they show you a case where I had water with particles and an oil at the top. And then if you look at the zeta potential of the particles, they were very high, about minus 70 or plus 40 in the top and the bottom respectively. And it turns out that if you have particles which are highly charged, no matter how hard you try emulsification, there's a complete phase separation. That is, I have a separation of an oil phase and water phase and whatever particle that you have, because they are highly dense, they kind of settle at the bottom. On the other hand, if you are at a zeta potential, which is close to the isoelectric point, or the conditions where the particles are least charged, as you can see on the image of the vial on the right, we get these very nice droplets. And as you can imagine, these droplets are reddish brown in color because they are stabilized by iron oxide particles. And if you do microscopy, you see these droplets in the inset of the microscopy image, and the image at the higher magnification tells you that these are whatever particle that we use for emulsification, they're essentially on the surface. So what I'm trying to say is that this Pickering emulsion is a very simple way of stabilizing interfaces, and what gives high stability to the Pickering emulsion is the formation of a layer of particle on the surface of these droplets. Okay, so that makes them really highly stable. And so we've been working on a particular concept where we are trying to promote this idea of using oppositely charged particles for Pickering emulsification. So if you have conditions where, what I mentioned here is that having conditions of less charge, okay, having conditions of zero charge or less charge is essential for Pickering emulsions, is what I was trying to convey in this particular slide. Other way of achieving less charge is by using particles which are oppositely charged. If I have a mixture of positive and negatively charged particles, if I put them in the right composition, it turns out that you get aggregates, and these aggregates are less charged compared to the original particles. And it turns out that if you do Pickering emulsions by using a mixture of oppositely charged particle, you can get very highly stable emulsions. So the picture on the bottom left is that of droplets. And because we were working with microscopically observable particles, we can look at what is on the surface of these droplets. And you can see that these are droplets stabilized by a mixture of 9 micrometer polystyrene and a 2 micrometer polystyrene, the combination of the two, 9 micrometer being negatively charged and 2 being positively charged. And the microstructure on the top right right side will show you that there's a kind of a dense packing or a close packing of these oppositely charged particles on the surface. This is what gives rise to very stable emulsions. As I mentioned, when I say that you take fluid 1, fluid 2, and particles and mix it, typically the mixing is done by using high energy mixers, for example, homogenizers and things like that. And it turns out that this is a very high energy intensive process, and therefore we've been asking these questions as to, can we come up with some new methods of emulsification? Okay, can I say that, hey, look, instead of doing high energy mixing, can I do something different? Okay, so in that context, we have kind of come up with a really nice and simple technique, and this is a published data. And so what we do is a very simple trick that we know that if you have a steam, and if you bring steam in contact with a colder liquid, we know it's going to condense, right? And the condensation is going to happen in the form of formation of these droplets. Okay, what we did is we took steam and then we bring it in contact with oil which contains particles. And these particles are dispersed in oil by some mechanism, for example. And then because you have a cold oil, the moment the steam comes into contact with the cold oil, is going to generate droplets, and then the understanding is whatever particles that you have in the oil, and if they are of right chemistry, right wettability, right conditions, you can stabilize these emulsions. Okay, that's the kind of thought. And what we did was we kind of generated steam by basically passing water through a conventional heater. For example, it could be your like say a furnace, for example, right? And then, so what you do is these are images of the vials in which what we did was we in the first case, right, the 90 degrees centigrade corresponds to the case where you're sending in hot water into the cold oil, and 110 and 130 corresponds to the case where I'm above the temperature where steam can be generated. Therefore, I'm looking at superheated steam, steam in a way. And then when we look at what is there in the bottom phase, okay, and if you just do microscopy, we saw that in the 90-degree centigrade case, where of course you're sending hot oil, and of course you get some droplets, but very, very, very small in number. But then if you look at 110 and 130, you get really large number of these are water droplets, and they were kind of stabilized by these particles. And one of the nice things about this technique is that you have a very close control over the distribution of droplets in your emulsion. Okay, you can generate emulsions which are of the order of about 14 to about 30 micrometer in diameter, which is very challenging if you look at high energy processes. And so you can do this as a batch process, where I start with a cold oil and then let the steam come in. That's one way of doing it. But the second way of doing it is continuous synthesis, in which what we were trying to do was, can we basically combine this steam generation technique, and then can we bring the steam in contact with a channel which is essentially carrying the cold oil dispersed with particles. And it turns out that you can again go from a batch mode to a continuous mode, and we were kind of able to generate droplets of, again, very small sizes by using this technique. Okay, so therefore, I think in my opinion, if somebody is thinking about methods to scale up the production of Pickering emulsion, the steam condensation is a nice way of doing it. And yeah, so in the next about 7 minutes or so, I'm going to tell you a little bit about combining the two aspects. This is a processability of Pickering emulsions and some sort of 3D printing. And so whenever you want to use this porous ceramics from Pickering emulsions, of course, as I said, you're going to kind of use Pickering emulsions or the particle stabilizer emulsions. Of course, your Pickering stabilizers are supposed to be, if you're thinking about, depending upon what kind of ceramics that you want to generate, your Pickering stabilizers could be silica, alumina, titanium, or mixtures of these two, depending upon what you want to produce. And so for that, I'm just going to demonstrate some examples where we were looking at generating Pickering emulsions by using fumed titania, that is a TiO2 particles, and which are kind of is fumed because it kind of has what is it called, fractal-like structure. And then you have a polymer. So in this case, again, I'm just trying to basically reiterate that we are looking at a system of positive and negative charged species. In this case, the particles are positively charged, and the polymer that I'm using is negatively charged. And we use these two in a particular mixing ratio, in this case 0.2. The 0.2 is because we would like to have very little polymer, because I want to produce a porous ceramic. Therefore, I want the porous structure to be more of titanium, not polymer. And then we looked at understanding the influence of pH. How does it, because pH is supposed to play a role in terms of manipulating charge and stuff like that, right? And again, as I said, the protocol is very simple. Take water, oil, mix these dispersants, homogenize it, and when you do that, you get these nice droplets. Okay, these are emulsions which are floating on the surface, right? These are oil in water emulsions, and the reason why they float on the top is because they are less dense, and you see that there is a clear water phase at the bottom. Okay, of course, these are not good for printing. Okay, because if you really want to do printing, then you need to think about working with emulsions which are highly I seem to have a okay. So because if you want to do 3D printing, what we want to do is to work with the higher particle loading. Essentially, you see, we looked at the picture that I showed you was a dilute case where we were looking at very small concentration of the stabilizers, but then the 3D printing requires a little larger particle loading, and then the technique that we are looking at is optical microscopy and rheology. And these are the emulsions that are formulated, and you can kind of by visually you can kind of classify these emulsions that are made at different particle loading, like 10 to 30, as liquid-like, self-supporting gel, and granular-like solid. This is a very visual way of doing it. And then if you do microscopy of these things, you see that all these formulations have droplets, and that's a frequency distribution of droplet sizes of the order of 10 micrometer. And that's the 3D printing. So this is done under particular conditions. Printing speed is fixed, and substrate is cellulose, and there's nozzle speed and things like that. And when you start printing the emulsions that we made, it turns out that depending upon what formulations you did, you get different printing, right? Because it just depends on the properties of the ink that you have made for printing. And the cases where I had a liquid-like dispersion or liquid-like emulsion, there was a flowing effect, because of which there's a coalescence. You really don't get a good quality print. But there's a certain conditions where we got a good quality print, and I'm going to explain a little bit about what the properties of those ink are. And then if the particle loading is very high, there's a nozzle clogging. That's basically permits you, prevents you from getting a good quality print because there's a choking of the nozzle during the process of printing. And the good quality printing, I think it was mentioned in the last couple of talks, is that if you really want to get a good quality printing, especially by this kind of extrusion-based printing, is that you need to have two characteristics. One is, of course, it has to be shear thinning. So what you're looking at is a picture of how the viscosity changes as a function of shear rate. You see that with the increase in the viscosity, with the increase in the shear rate, the viscosity drops down. That's one important aspect. And the circles that you're seeing on the leftmost plot are the conditions that corresponds to the rest state, okay? Because when you have your ink in the syringe used for printing, it's at a rest state. Therefore, the shear rate is very, very low. But then when you're plunging it, right, your viscosity corresponds to a slightly higher viscosity of about 300 reciprocal per second. Therefore, what is important is what is the viscosity of your ink at the rest state, and what is the viscosity when it is coming out of the nozzle. Plus, another important characteristic is that as soon as you stop printing, your viscosity should go up, right? Because if it doesn't go up, then there's going to be this coalescence, sagging, all those effects are going to come into picture. So that's one of the key for the formulation. I can spend a little bit more time on it if there's an interest in some of you. So what we did was, as a function of pH and particle loading, we kind of came up with this map of visual observations of where the printing is better. That corresponds to these green lines, and then we could do rheological measurements and then identify that for good quality printing, you're going to have the modulus in the range from about 15,000 pascal second to about 35,000 pascal second. That's a kind of a key number for the printing application. And once we did the printing, what we were able to do is to take this printed structure and we were able to sinter it and get some nice porous structure. And we could decorate them with gold, for example. These are printed structure, porous ceramic, and then decorated with gold. And then we were able to show that there is deposition of gold on the surface. And I'm just going to stop with that talk, and then I'm going to say that pickling emulsions are versatile templates for making porous materials, and there's a lot of interest in making different kinds of ceramics from this technique. Yeah. Thank you so much.
Thank you very much for your talk. Is there any questions related to the talk? So I was very intrigued about your last results which you showed. Can you elaborate a bit? We still have half a minute. Sure. Related to how you control this shear thinning behavior and the fast recovery which are required.
Sure. Right? So in this case. As I mentioned, right, typically whenever you, even in the conventional porous material fabrication, the characteristics of the gel are important, right? Because whenever you want to shape it into whatever structure or the size of the mold that you want to create, right? So in this case, what we are trying to do is we had droplets, right? On the surface of these droplets, you had particles, right? And then in between the droplets also we had a network. This is a network of particles. Therefore, in this case, what we were able to do is we kind of exploited the interaction between so we were able to embed the droplets stabilized by particles in again a network of particles, and that's what was the key for this particular application. Yeah.
Thank you. Thank you very much. Let's thank again for the nice talk.
Thank you.
And then please let me just
sure.
hand this memento to you.
Thank you.
So we will move now to the next contribution, which will be an invited lecture. given by Dr. Maxence Pujol from 3D Ceram Cinto from Limoges, France. He will talk about an innovative approach to additive manufacturing of technical ceramics, and we are looking forward to your contribution, Dr. Pujol.
Thank you. He's coming. Okay, so good morning everybody. Very glad to be here today with you. So my name is Maxence Bourgeol, ceramic engineers and sales manager for the French-based company 3D Ceram Cinto. First of all, a big thanks to Ravi Kumar and all the organizing committee for giving me the opportunity to have this speech today. It's not my first time in India, it's not the last time, but it's always a pleasure to be here. Today, I would like to speak about an innovative approach for the additive manufacturing of technical ceramic parts. What does it mean? I will not really be focused on the hardware, the process, the material, and so on. Today, I really want to highlight some industrial application whose already adopted ceramic 3D printing, okay, for which application can be used additive manufacturing of technical ceramic parts. First of all, very quickly, some few words about our company, just to set the context. So 3D Ceram, as I explained, is a French-based company created 22 years ago. So we are only focused on the additive manufacturing of technical ceramic parts. Our first business model at 3D Ceram was to print, manufacture technical ceramic parts. And end of 2015, we decided to change the strategy to provide printing line to our customers. Printing lines means the software, the hardware, so the printer, the material, debonding furnace, sintering furnace, and so on. And since 9 years now, so we develop a wide range of machines with SLA, stereolithography technology, in order to meet almost all the customer needs. So as I explained you, 22 years of experience only in technical ceramic 3D printing. We are 60 people globally. We have some office, as you can hear, in French, Limoges, small city in the middle of France, but well known for ceramics. We have some facility as well in the US, in China, in Japan. And Cinto, a Japanese company, became our main shareholder end of 2017. So Cinto, very quickly, it represents, so Japanese group, almost 5,000 people all around the world, 1.3 USD billion of turnover. And to have a shareholder like Cinto, I would say it can allow us to expand faster our activity, and it gives confidence to our industrial customers in order to consider 3D Ceram as a partner and not only a supplier. So I'd like to say that 3D Ceram, we are a process provider. Process provider, what does it mean? It means that we develop solutions for each step of the process. We develop, obviously, printer. I will explain you after which technology. Software as well, specifically made for technical ceramic 3D printing, for instance, in order to scale the parts as we have shrinkage during the sintering step. The slurry, so what we are calling mix, which is really a mix of ceramic powder and photosensitive organic content, and some services. As Martin from Litos explained, 3D printing is not a press button process. So we still have to share the know-how to allow our customer to print as quickly as possible some good technical ceramic parts. So since this morning, we are speaking about 3D printing, so I will go through very quickly this slide. At 3D Ceram, we develop and we use SLA, stereolithography, which is a top-down process. So the two first steps of the process are common for any additive manufacturing process. First of all, you have to create the CAD file of the part that you want to print, and then you have to generate the printing platform, which means how many parts on the printing platform, printing orientation, and so on. After, and I will show you a video after, with top-down and SLA process, we print the part layer by layer to the bottom to the top. So the material is a slurry, okay, low viscosity slurry, mix of ceramic powder and photosensitive organic content. A blade spread a thin layer of slurry on the printing platform, and we have one or several UV light, UV laser on the top, who cure the area to print. And again, in order to print, to shape all the ceramic parts, layer by layer, to the bottom, to the top. After printing, we have to save the uncured slurry, who can be obviously reused for the next printing run. And then, as for any technical ceramic process, we need to debind and to sinter the part to obtain a fully dense ceramic part. So we develop a slurry process, low viscosity slurry. So we develop low viscosity slurry to make easier what happened after the printing run, how to save the part and how to save the uncured slurry. And this low viscosity slurry will be printed layer by layer by the SLA machine. So the blade spread a thin layer of slurry on the printing platform. Layer thickness, of course, is depends of the slurry and the customer need, could be between 10 micron and 110 micron. And the UV light, UV laser, based on the top of the machine with a wavelength of 4 or 5 nanometer, will cure the area to print. Then the printing platform will go down of a layer thickness, and so on and so forth, in order to print, to shape all the ceramic parts to the bottom, to the top. After printing, here you can see, for instance, some foundry course for investment casting. So we remove the printing platform, all the uncured slurry stay in the machine. So after we have to clean the part, it is called the cleaning process. So we blow compressed air and solvent, and then, as I explained you, as for any process, we have to debind the part and to sinter the part into furnace, oven, to obtain a sintered part. So this morning we had some nice talk about the DLP process. No misunderstanding. I'm not here to say SLA is the best process, blah, blah, blah. There are no almighty process, in my opinion. Each process, each additive manufacturing process have pros and cons. With SLA, which is a top-down process, I like to say that the gravity is with us. So we don't need physical links between the part and the support, or between the part and the printing platform, for instance. Then, as we are using UV laser and not DLP, voxel, we don't have the voxel effect, so we can print some more accurate parts. But in my opinion, one of the most important strengths of SLA and top-down process is the fact to be able to have big printing platform. So with SLA, you don't have any limitation for the size of the printing platform. If you increase the number of UV laser in the top, you can increase the size of the printing platform. So we develop a wide range of machine until 600 per 600 per 300 mm. This big printer for the additive manufacturing of ceramic parts can obviously be used for the printing of big ceramic parts. For instance, here, I would like to show you an alumina mirror print on the big machine, so diameter of 500 millimeter, used for space application. The printing time of this part was roughly 23 hours. So this is why I would like to show you the 3D printing. Since this morning, we mainly see small parts, which is obviously one of the main advantages of 3D printing. But keep in mind, and this is why I'm here today, it can also be used for the printing of big, fully dense ceramic parts. And it can also be used for the mass production of ceramic parts. During years, I heard that 3D printing was a nice process for prototyping. It's a nice process, but only for small part, prototyping, and so on. It is true, but since years, and this is what I want to highlight after, we have some company, industrial partners, who start to use 3D printing as a production process. So 3D printing will never compete with CIM, for instance, ceramic injection molding process in terms of productivity. But for some series of thousands, 10,000 of parts, it's not possible to use 3D printing to reach some target for the production cost of parts. The mix, so the formulation, mix of ceramic powder and photosensitive organic content, is one of the most important points of the process. So the user has 3 options. They can use a standard mix developed by 3D Ceram for alumina, zirconia, HAP, TCP, and so on. We can also develop an on-demand slurry, or all the machines are open. So we have some customers, some users, I will show you after, who develop by themselves some nice slurry, nice printing parameters to print some ceramics that we are not able to print at 3D Ceram. At 3D Ceram, for the standard formulation, we mainly provide oxide and non-oxide. I will show you after some application, alumina, zirconia, hydroxyapatite, tricalcium phosphate for implants, and nitride, aluminum nitride, and silicon nitride, mainly for space application. But, as I explained you, we have some customer user who develop by themselves some nice slurry for some nice application. I want to highlight some of their success. I have a customer in Singapore, for instance, who developed a formulation for spinel. Spinel is a transparent ceramic who can be used for defense and luxury as well. YAG, alumina with short fiber of silicium carbide, for instance, to increase the mechanical property. SiC, piezo, ferrite, all this formulation, all this very specific technical ceramic was developed not by 3D Ceram, by our customers. So now, and it's really what I want to highlight today, I want to show you some application who already adopted technical ceramic 3D printing, not for prototyping, for real use case. First one, implants. Everybody is speaking about implants, but it is already used or not? In our company at 3D Ceram, so we are based in Limoges, as I explained you, we printed skull implants since 2005. HAP cranial skull implants. The advantage of 3D printing is obvious, because nobody has the same defect. But on top of that, on the same part, you have three different functions. You have the dense area in the middle for the mechanical property. You have some macro porosity on the outside of the part to allow the osteointegration of the implants. And you can see some big hole all around the part to allow the surgeon to attach the implants with bioresorbable wire. So it's better to see this slide before lunch than after lunch, but it's very important for me to show you that it is not only a slide. It's not only to say it is possible. It is a reality today to use HAP printed skull implant for real human patients. We did the clinical certification between 2005 and 2009. And between 2010 and 2015, we printed more than 50 skull implants for real human patients based in our city. So maybe some of you knows well titanium skull implants. So the question is why some surgeons prefer to use HAP skull implants? Because you have a perfect osteointegration of the implants with HAP. What you can see on the CT scan, 12 months after the surgery of the HAP skull implants, you don't have any gap between the skull and the implants, which means that the real bone created some link in the implants. So the osteointegration is perfect. Obviously, as it is HAP, you have a total biocompatibility of the implants, and you don't have any risk of rejection of the implants. With titanium, you have some case where the human body rejects the implant. This morning, we quickly spoke about dental implants. Yes, it is possible to use ceramic printing, and especially zirconia with 3Y, 3% of yttria, for dental implants, for zirconia screws or zirconia crowns as well. Another exciting application for 3D printing is space. Everybody is speaking about space, but ceramic 3D printing is mainly used for what I'm calling new space. Small satellites who go at low Earth orbit, at approx 400, 600 kilometers to the Earth. The part on the top that you can see is an antenna for telecommunication. They need ceramic and they need zirconia due to the permittivity of zirconia, and they need 3D printing and SLA for the complex lattice structure. These customers already obtained the space certification a few years ago, and they already launched in the space hundreds of antennas made with ceramic printing. So today we already have in the space some ceramic printed parts. Same things for the part in the middle that you can see. The device in the middle is called a thruster. Thruster, it is an in-orbit propulsion device in order to change the trajectory of the satellite in the space. Inside, I cannot show you the design of the part, but you have a very critical alumina part, very complex part. And they already obtained the space certification, and same things, they already launched tens of satellites with thruster with alumina printed parts. This morning, we had a very nice talk by Applied. Semiconductor definitively is a very hot topic for ceramic, including ceramic printing. They need, so obviously we are not printing the chips, the small chips, but in the machine to manufacture the semiconductors, they need big alumina parts. And they start to use additive manufacturing and 3D printing in order to produce locally the big alumina parts and to add some function in the parts. So you can see on this slide some example of gas distribution ring, suction plates, and robot arm. Some of these parts are already used by some customers, especially in Asia, for the manufacturing of semiconductors. The topic of the event is ceramic for sustainability. So for me, it was really important to highlight also one of our last development for the production of hydrogen, production of green hydrogen, especially by SOEC, SOFC. One of the main components for the production of hydrogen is a part made with zirconia with 8% of yttria. Right now, it is already used, certified, and they use tape casting process to make a plate, flat plate of zirconia. But they start to consider and they start to use 3D printing and SLA to change the design of the flat plate and to make this kind of plate, cell with corrugated design, with wave. And if you have this kind of design, you can increase the mechanical property, you can increase the surface area of the device, and you can functionalize the part, which means you can add some function in the same part. So all the technical aspect was okay. For instance, here you can see 6 parts print on the medium-sized machine. But as I explained you a few minutes ago, the technical aspects are not enough. What we want to push at 3D Serum is the industrialization of the process. It was not possible to reach the technical cost, the target for the production cost, only with our big machine. So what we decided to do with the customers was to develop an on-demand printer. So what you can see here is not yet on the market. It is a bigger on-demand machine for the mass production of the zirconia cell. Inside, you have 6 UV laser, 2 printing platforms printed on the same time. Just the goal is obvious: increase productivity, decrease production cost. This customer will start to use the machine within few weeks, as from January 2025, in order to produce 100 of zirconia cells per week. So I spoke a lot about industrial, but there are not industrial without students who want to work in technical ceramic 3D printing. And this is why at 3D Serum it is also our target to democratize additive manufacturing of ceramic for most of the students. This is why we develop this smaller machine, which is not a SLA machine. It is a versatile machine based on extrusion process. So the same machine can use different extrusion process, FFF, pellet extrusion, robot casting as well. And one of the main advantages for the technical aspect is to print SiC. So we had a lot of discussion about SiC this morning. Martin explained, which is true, that it is very complex to print SiC with SLA or DLP process. This is why with FFF you don't have any limitation. It is an extrusion process. So what we can print for SiC, for instance, we can obtain a density of 97%. As you might know, one of the limitations of extrusion process is the surface aspect and the density of the part. This is why recently we upgraded our extrusion machine with a milling system in order to be able to machine the part during the printing run. If you mile, if you grind the part during the printing run, you can improve the surface aspect and you can also increase the density of the part because most of the porosity are based at the outside of the part. That's all for me, thanks. And if you have any question, obviously do not hesitate to ask. Thank you.
Thank you, Dr. Bojol, for your nice talk. Is there any questions related to the talk of Dr. Bojol? So people seem to be very happy.
If you have questions after,
no questions,
I have a booth, so do not hesitate to come.
So don't hesitate to pass by at his booth and talk to Dr. Bojol.
Exactly.
Thank you again for your talk.
Thank you. You have a gift as well?
Yes. So we move further in our session. We will have now a series of contributor talks, and we are looking forward to the first contributor talk given by Mayank Mishra from IIT Madras, and he will report on biaxial compression strength testing of additively manufactured aluminas. Mayank, stage is yours.
Thank you. Hello, good afternoon all. So myself Mayank Mishra, I'm a research scholar at IIT Madras. I'm working with Professor Ravi Kumar. Today, title of my talk is Biaxial Compression Strength Testing of Additively Manufactured Alumina Ceramics. We are using a novel approach and doing some geometry optimization also. So as we have seen, the additive manufacturing, we are making a lot of complex shapes. The complex shapes, what we are making, the main issue with the additive manufacturing or what we face is the anisotropy. So when we make complex shapes, they go under the complex loading condition. Now, if you want to understand how the mechanical properties are changing when we are going in the complex loading conditions, we need to do some testing. So the closest complex loading what we can do is the biaxial testing. So we do have a lot of printing methods starting from stereolithography to SLM, but not all are used for ceramics, but most of them have been now used for ceramics too. So what I have used is FFF, fused filament fabrication, which he just now explained. And I'll be using alumina ceramic, which is supplied by a company called Zetamix, and I use the printer which was given by the Raise 3D printer. Okay. So first, before going to the biaxial testing, I wanted to understand what is happening at the for the uniaxial samples. If I am printing it in the different orientation, and if I am doing some compression test. So I've printed 5x3x3 dimensions. Now these dimensions are specific to the machine what I'm using for the testing, that is made by the in situ micron. So this geometry was optimized for testing the ceramics in that machine. And the printing parameters I used was like I used the layer thickness of 0.2 mm, kept nozzle temperature 150, and say some printing speed of 20 mm per second. And I did scaling like this. This was supposed to be the final dimensions. So as this has the polymer in it, after printing, debinding and sintering, it will shrink. So this was already given by the filament supplier. So I used the same scale. I scaled it up and then printed. I printed two types of sample, vertical and horizontal. Going next, while we were debinding it, there was an issue, like as we printed very small samples, this has to go in two debinding steps. First the chemical debinding will happen, and then the thermal debinding will happen. So while we were doing the chemical debinding happens in acetone, and we have to do ultrasonicate for say 30 minutes or more. While I was doing for very small parts, they were breaking. And even in the from the data sheet also, they're saying the minimum part size should be 6 mm cube in any direction. So mine was even smaller than that. So while I was doing debinding, they were failing. So I thought, let's skip the chemical debinding and see how the thermal debinding happens. Before that, I wanted to do some studies regarding to optimize the debinding process. So we did TGA, where we found that resin is getting off between 250 to 510, and around 85% is the ceramic loading. And the dialectrometry data showed like sintering starts at 1475, but as the machine had the limitation, I could not see exactly the sintering temperature. So I printed different sintering, I printed different samples and different sintering temperatures. So this is the sintering cycle which I followed from, so the debinding step was almost same for everyone, but the sintering temperature I changed from 1475, 1520, 1550 and 1600. And then after sintering, I did the XRD and found out that it had alpha alumina. Even before sintering, only as printed part I did, and you can see the background to intensity ratio, where you can see because of the presence of polymer, the intensity has decreased. So these were some compression test results where I'm plotting against the time here. So if you see here, just a second, where is it? Yeah, so if you see, I've plotted against the time because the machine I'm using, there we are measuring the strain using the DIC method. So where we do some speckle patterns and then measure the strain. So while measuring the strain, there was some anvil movement. And because of the anvil movement, the camera was losing the focus. So the strain capturing was becoming very difficult. So and even though I just wanted to see how much load each sample can take, so we could see like it is failing. Like you can see drops in the curves. Those drops are some cracks that are happening along the way. So to find out what could be the reason of these cracks, I looked at the looked in SEM of microscopes of the samples, and I found out that the interlayer bonding is not that good. You can already see the interlayer bonding is, you can already see the lines, vertical lines there. And again, the surface finish is not good. And down there in the below image, you can see some dots are there. Those dots are because while printing, we first print the outer boundary and then do the infill in this one. So after we print the outer boundary and then do the infill, the infill layer is perpendicular to the boundary. So there is one hole or gaps there, which you can see in the bottom picture. Yeah, so for all these things, I've used the machine by Institute Macron, which is used for the in-situ testing, which can do all biaxial, uniaxial, and also fracture studies. So after those samples failed, I looked at the fracture surface of the samples, and you can see this, at 1600, the grains were very fine. At the grain size, you can already see it is changing, and at 1600 the grains were very large compared to 1475, 1520 and 1550. And yeah, and now when I wanted to do the biaxial testing, because of the anvil movement, the sample was moving. So we thought, let's optimize the geometry and bring it to something which will not move, and that's why there also, if you see for the biaxial testing, the square geometry would be the ideal. But if you want to restrict the anvil movement, you have to either cut the anvil or you have to cut the samples. So anvil cutting, both of them will result in higher stress concentrations. So anvil cutting would not be a good idea, because otherwise if it fails, you have to replace it a lot. Because we can print any shape here, I thought of going for sample optimization. So I took the 1/4 of part and then did some FE analysis. Yeah. So we did first meshing, and then I tried 3 different types of cuts at the border. One was sharp, fillet, and rounded. All of them gave very high stress concentration values. So rounded was still better, but the stress concentration was still high. And then I moved to the topology optimization of the shape. There, the stress concentration was low, the stress value was low, concentration was low, but still the size of the sample that was coming was around only 1.5, which is in the contact with anvil, that was only 1.5. So I could not go with it, because this will again result in the movement of the anvil. So again, the optimization I did using 2 different profiles, the spline and elliptical. If you see spline profile, the d is the distance between the d is the distance that I'm varying, And in the optimization, you can see the minimum stress was coming at 0.4, and the KF ratio was only 1.48. But with this geometry, the issue is if I move even there is a 100 micron difference in the while manufacturing it, there will be a lot of change in the stress value. In the elliptical profile, it gave better results. There were two radius, and the optimized load came to stress came to 956 MPa, and that is the geometry I used. Coming to the conclusion side, the further testings will be done. Like I'll be doing the testings now. I've done till this part. So these are the conclusions. These are most of the points I have already mentioned. Thank you so much. I would like to acknowledge laboratory for high performance ceramics. This is our lab and our group. Thank you so much for your attention.
Thank you, Mr. Mayank. Due to the fact that we do not have time, we will skip the questions, but hopefully you will be available if any questions in the high day or something.
Thank you.
Thank you for your talk. Let us move to the next contributed lecture in this session, which will be given by Polly Rose. He is from University of Hyderabad in India. He will report on fabrication of complex shaped ceramic bodies combining AM and gel casting technique.
Good afternoon all. Myself, Polly Rose, a research scholar from University of Hyderabad. So today I will be talking about the fabrication of complex shapes of ceramics by combining additive manufacturing technologies with gel casting. So this is my outline of my talk. So first I will talk about, give a brief introduction on gel casting procedure. Then I will go on to the how I combined complex additive manufacturing techniques with gel casting to produce complex shapes. Then third, I will talk about the usage of non-toxic binder for gel casting technology. And finally, the direct ink writing of ceramics. So gel casting is a slurry-based shaping technique which is invented in 1980s in USA. So the procedure starts with the making of a slurry, which is a mixture of binder, ceramic, and a solvent. So this will be mixed, and the slurry will be poured into a mold, and the polymerization happens, and after this, the mold is removed, and binders are removed by heating and finally sintering to get the final shapes. So as you can see, our shapes are mainly depends on the mold we make. So initially when we started working, we used our materials which are locally available like plastics, aluminum, and styrofoam for the as the mold material. So these poses limitations such as we were unable to get required shapes and some other limitations also. So we thought of combining our 3D printing technologies to make the molds. So we used filament fusion technique, which the earlier people has already explained. So we used ABS material for the fabrication of mold. And with this, we were able to make molds with very minimal thickness, and we were able to get very nice products. We used alumina powder for the fabrication, and this here you can see the first is a CAD model of the mold, and white one is the B is the mold printed, and the third one is the sintered alumina block which we got. And other shapes also we were able to make. And when we examined the mechanical properties, it was fantastic, like flexure strength of 389 MPa and fracture toughness of around 3 MPa rotum. And these are some of the shapes we were able to make in our lab. And one of the limitation with this procedure was the use of toxic binders, which are acrylamide based, which are MAM and MBAM. So as an alternative to this, we used isobam, which is a non-toxic binder, and it has added advantages as it can polymerize at room temperature and it can both act as a dispersant. So we used this isobam binder and fabricated tungsten carbide cobalt shapes. We have made identical shapes using MAM and acrylamide based binder and isobam and compared its properties. And the properties were very comparable, and we were able to make some good shapes. The right one is a cup shape, which is used as a insert, ball mill insert in the high energy ball mill. And moving to the next, the extra step involved in the procedure is the mold making, which can be avoided by fully printing the slurry. So we thought of making our gel casting slurry into a little more thicker by increasing the viscosity or the loading of the powder. And we made an extrusion setup, and which is our thicker slurry will be filled in the syringe, and that will be extruded through the nozzle. And this is attached to a XYZ stage, which will be moving around according to the design and printing our design. So since we are going with the high loading slurry, the optimization of slurry loading is very important. So when the slurry is very thin, the structures used to collapse after some amount of layers of printing. And when the loading was very high, it used to create non-uniform flow, and it created defects such as pores and protrusions. So we optimized at 56 loading, and we used to we were able to print some of the shapes, which is around 8 centimeter dia, a prototype for the turbine blade. And one of the limitation, and we have examined the properties, like since the printing is happened by layer, the complete merging of two layers is very necessary, crucial. So we have examined the green body, and we took the SEM image, and we can find that the layers are merging completely, and even after the sintering also there is no delamination of layers happening. So we examined the properties in both vertical and horizontal direction, and we found that we printed in two directions, one in a rectangular place and in a pyramidal shape, and we cut the samples for flexural strength, and we measured it, and in both directions we were able to get somewhat close range properties in flexural strength and fracture toughness. And comparing to the gel cast product, as cast product, it was the values were also equally good. And another issue with the layer by layer printing was the surface roughness. So since it is printing by layer, the surface roughness is an inevitable thing. So to get a fully finished product, so we were tried using a CNC machine so that the same design can be used to surface polish the printed product. So we were polishing it at the green body stage, and we were able to get very good surface polished products. So this is the printed product, and the other one is the after polishing. So polishing is done at green body stage, so it is very easy to machine, and the leftover powder can be reused also. So then we wanted to try it into another systems also. We extended this to yttria stabilized zirconia. There also we have examined the microstructural properties, like how the layers are merging together. So with yttria stabilized zirconia also, we were able to get really good prints, and we were able to get good nicely packed grains, and density was also very good, around 98.2%. And the flexural strength were measured in both direction in this case also, and it was also there was a difference around 17%, and in case of fracture toughness it was just 5%. So by slurry-based deposition technology, we can the main advantage is the ability of the procedure to make bigger shapes and relatively fast production of printing shapes. So comparing to other photopolymerization printing techniques, it has a limitation in printing very complex shapes, and surface finish is there, but still it has the ability to print very bigger sized shapes with very minimal time. So these are my conclusion, which I have already told, and I acknowledge my professors and co-supervisors and my group and university and my collaborators for the talk. Yeah, thank you.
Thank you for your talk. Any urgent question for Mr. Rose? Seems not to be the case, but you will be available if any question. Thank you again for your talk. We move to the next contributed presentation, which will be given by Mr. Swapnil Stok. He is from CIMET in Pune, and he will report on fabrication of complex shape ceramics body, combining rapid and low-cost fabrication of customized multi-layered and multi-material LTCC electronic circuits using DLP. So, Mr. Doak, stage is yours.
Good afternoon, everyone. Myself Swapnil Doke, and today I will be speaking on the rapid and low-cost fabrication of customized multi-layer and multi-material LTCC electronic circuits using the DLP 3D printing technique. So I'm from CIMET Pune. We have Electronic Packaging Division and the Center of Excellence on Additive Manufacturing, sponsored by the Ministry of Electronics and IT. So first I will highlight what is the LTCC technology and why we are using DLP based 3D printing for this LTCC based electronics. Then I will move over the rapid and low cost fabrication of the multi-layer circuits. So basically, CIMET is working since last 20 years on the LTCC techniques. It is the one of the first lab in the India in which CIMET has developed the LTCC based electronic packaging state-of-art facility. CIMET has developed many packages for the defense, DRDO, ISRO, BRC in terms of electronics and micro fluidic applications. So basically this LTCC technology is nothing but the multi-layer glass ceramic packaging technology which has a wide application in the field of space and another terrestrial applications. So these are some pictures of the facilities. I'm not highlighting on these points. So basically the comparison of this LTCC technique with the 3D printing, that is the additive manufacturing technique, is that in the LTCC techniques there are many steps which involves for the final production of the package. So which includes initial material like green tapes, wire punching, printing, stacking, lamination, and finally the co-firing to remove the organic parts. So these all steps require number of machines and the huge time for the complete packagings. So this one of the drawback of this techniques. So we are currently new or younger in this DLP technique, so in which we have tried to minimize the drawbacks of these systems, and the single 3D printer can be used for these complete steps. Only the post-processing, that is the co-firing, is required. So in which we can save almost 80 to 90% time and the investment. So this Center of Excellence on Additive Manufacturing developed at the CIMET Pune has a objectives to fabricate the DLP-based 3D printer, development of LTCC materials, and demonstration of the 3D printing LTCC-based low-cost fabrication packaging technology for optoelectronics devices. So these are the this is our 3D printers. So this is a 100% indigenously developed 3D printers in which the DLP technique is used for the printing. So what is the DLP technique? DLP technique is the digital light projection based. So it is one of the additive manufacturing techniques in which the wet polymerization is used. The advantage of this technique is that the single layer is cured at a time. So the speed is very high as compared to other 3D printing techniques. So in which we are taking the photopolymer that is in liquid form to cure the in the solid form. So the basic process flow is given above. Only, first we have to make the materials, that is the photopolymer and the different functional material depending upon the design and the application. And first we have to make the 3D design by using the CAD software, and by combining this solid hardware of these 3D printers, we will get to the structures. This is the materials used for this DLP 3D printings. There are different functional materials which includes different conductors, dielectrics, sacrificial materials. So these materials are functional materials. These are used in the photopolymer to get the particular viscosity for the DLP machines. So characterization is done to confirm the size and the structure. So as I have mentioned that we are just a little bit younger in this DLP technology. So first we have tried to print the different kinds of features that are involved in the DLP 3D the electronic packaging system. So we have printed different structures like line, wires, circular pads, micro channels, and cavities to show the capability of our 3D printer and the compatible materials for these 3D printers. So our 3D printer has a optical resolution of 50 micron. So we can get up to the 100 micron conducting lines and around 300 micron channels for this 3D printer. So then we have moved over the proof of concept package. So initially we have tried 3 packages. First is just to show the capability of multi-layer and multi-materials 3D printer. That is a POC one. It is named as. Second one is used for the optoelectronic packaging, in which the electronic packaging that we have expertise, and in which we have to incorporate optical chips by optical packaging technology. So we have to merge that optical packaging and electronic packaging in the second POC. And the third one is the just demonstration of one of the electronic component which is majorly used in the RF technology or macro electronics, that is the directional couplers. We have referred one manufacturing many circuits. From that we have taken the design and we have made the dielectric base. So once it is fired, we can connect the ferrite core and we'll test it the device. So this over to this summary of this works, we have actually developed the materials for this 3D printing technology, which includes the LTCC dielectrics, silver and silver palladium conductor materials. We have optimized the composite preparation for photopolymer based on the in-house prepared LTCC, AG, AGPD and commercial graphite for the suitable for this our 3D printer. And this 3D printing process is set up for single material, multi-material and multi-layering features, and for the fine tuning of the parameters. In future, actually, we are working on the material properties to get the smaller size for the upcoming printer that we are developing for higher resolution. So that testing of all the materials will be developed, will be carried out once the fabrication of second printer is completed, and the centering and testing of the POC that we have printed that we will do in future. So these are some of our publications we have submitted in patents and research papers related to the materials and the process. And last one is the actually I have to highlight the things here that we have developed the materials process as well as the printer, all are indigenously. So that is the one of the benefit, and it is the objective of our center that we have to develop the self-sustained center in the India to for the additive manufacturing. So that we are working. I like to acknowledge Ministry of Electronics and IT for the financial support for this development of center. And also I like to acknowledge the organizers of this conference to give the opportunity to present our work here. Thank you. Thank you.
Yeah, thank you. Thank you for your nice talk and informative. Is there any question for Mr. Swapnil? So I would have just a curiosity question for the last minute we have. So you mentioned correctly that if you would be able to use this multi-material approach to 3D print the LTCC, this will be an improvement as with respect to the traditional way of processing. Did you have an estimation about whether the costs will be reduced?
So the cost reduction factor is main is the loss of the materials. Here actually it is additive manufacturing technology. So here as compared to the other 3D printing technology and the conventional methods, the loss is minimum. And additionally, as it is the DLP technique, that is the single layer is curing at a time. So the time is also major parameters. So we are saving this material as well as time. So the cost is finally reducing.
Some other questions for Mr. Swapnil? This is not the case. Thank you again for your talk. Before the lunch, we will have a last contributor talk. This will be given by Ms. Aishwarya Anil from IIT here in Chennai. She will report on breaking boundaries in ceramic fabrication, mastering macro to microstructures with DLP technology. So, Ms. Aishwarya, the stage is yours.
Yeah. Good afternoon to one and all. Myself, Aishwarya Anil. I am working as a research scholar at Vellore Institute of Technology under the supervision of Dr. Raghukiran Nadampalli. So today my topic is breaking boundaries in ceramic fabrication, mastering macro to microstructures with DLP technology. So I'll be telling an introduction, DLP principle, then the experimental part, result and discussion that we have achieved, what the results we have achieved, and conclusion. Yeah, so imagine a world where we can design, create anything that we can dream of, like a custom prosthetic hand that fits like a glove. Yes, imagine an airplane part which is both lighter as well as stronger, or an entire building which is printing layer by layer just in matter of days. So this is not just our future, it's happening right now. So thanks to the transformative power of additive manufacturing technique. And today, I would like to invite you to explore the fascinating world of additive manufacturing technology, that is especially digital light processing, DLP. So I would like to say, before going into my work, I would like to say the principle of DLP work. So we'll create a digital model and we'll slice it in a slicing software so that it will divide it into layer by layer manner, preparing it for printing, and then position the build platform so that when the projector projects the UV light, the resin will get cured instantaneously and thus get printed. The main mechanism which is happening inside the vat is photopolymerization reaction. So inside the resin, there will be a photoinitiator, monomers, and oligomers. So what happens is, initiation will happen when the light is exposed, UV light is exposed to the resin, so that the photoinitiator will, photoinitiator will be converting it into photoradical. So the radical, which is very unstable and will react with a monomer or oligomers and form a polymer chain molecule, and finally it instantaneously get cured in a layer by layer manner so that we will get a cured photopolymer. So coming to the experimental part, I have chosen alumina powder for my preparation, and then I mixed it with the resin, and we have given the CAD model to the printer so that it gets printed in a layer by layer manner, and we got macro to microstructures, which was very challenging for us. So the printed ceramic part is, first of all, it is called a green body, will be consisting of polymer, some solvents, as well as a ceramic part. So the second step is debinding step, that we have to debind it chemically. So after debinding, we will get a ceramic part alone, which will be which has to be densified through higher temperature, like 1550 degree or 1600 degrees Celsius. So the photopolymers and reactions that has happened here is like bisphenol and epichlorohydrin has reacted to give epoxy resin. In that way, we have used some organic molecules or organic compounds which reacted and form epoxy resins, acrylic hybrid resin, acrylated polyol resin, methyl acrylate resin, and finally we use phenyl bis 2,4,6 trimethyl bisphenol phosphine as a best photo initiator, and these these polymers which are acting as a backbone structure, cross-linking agents, as well as it also improves the mechanical stability and mechanical stability of the cured material. Then it is very suspecting that how the alumina particles are compatible with the resin. It is of course because of the physical adsorption and chemical adsorption. Physical adsorption means the ceramic particle will be covered with the resin. So there will be an adhesion of the molecules, like adhesion between the ceramic particle and the resin. Also some chemical adsorption. So the functional groups which are present inside the resin will react each other, and there will be a chemical adsorption, chemical reaction that can happen in between them. Also the hydrogen bonding, covalent bonding, cross-linking interactions will help them to make it to give it more curable or stable, and also most importantly steric stabilization is very important, which can be achieved by adding appropriate amount of dispersant and a suitable dispersing agent. So in my experiment, I started the solid loading of alumina from 40 weight%, and till now we achieved it to 80 weight%. So the challenges which we were facing was a delamination, then staircase effect, surface smoothness were first the challenges in our experiment, and we found that all these can be improved by improving the solid loading as well as the optimization of the printing parameters as well as optimization of the resin or the slurry which we prepared. Of course, we know that in most of the DLP machine, the UV visible absorption spectrum, which will be, or the absorption will be in the range of 405 nanometer. But this won't be the case when we add ceramic particles to the resin, because as we know that the particle, since the particles are there, scattering will be there, of course. So, and this is also because of the refractive index difference of the particle as well as the resin. So, because of this reason, most of the light will scatter instead of transmitting, and then the absorption will be more rather than transmission of light. So, one of the other factor which we have to see is the cure depth of the resin. This is one of the important parameter that we have to consider during DLP printing, because if this is not appropriate, then we won't get a nice quality product. So cure depth is nothing but the maximum thickness of the material that can be effectively cured by the light exposure, which is often measured in micrometers or millimeters. So by optimizing this, we can avoid delamination kind of defects in our samples. TG-DTG analysis has done, which is to make the sintering profile of our samples. So we have found that a complete decomposition of organic binder has achieved even at 450 degrees Celsius. So these were some of the complex parts which we tried to print, and we print kind of very complicated structures from macro to micro levels also. So these are the optical microscopic images where you can see the layer lines even. Of course, light dispersion and overexposure can lead to the quality of the material, and of course DLP lacks resolution limitations, but still printing parameters sometimes may cause such kind of defects or problems. Then optical microscopy of the images is shown here, and the optical microscopy, it shows that the green body and the sintered body differences that you can see from the figure. So in the first figure, you can see the green body, and you can find out the difference in the second figure that it has shrinked after 1550 degrees Celsius 4 hours. Then the shrinkage of the samples is, we have optimized it actually from 60 weight% to 80 weight%, and it has considerably reduced from 60 to 80 weight%. Of course, X-ray diffraction analysis shows that there is no secondary phase has formed during the reaction, sintering or anything, and the phase remains unchanged even after the complete sintering of the samples. This is a microstructure of the materials. For green samples, you can see some agglomerates here and there, but which we improved after our further processings. This is the microstructure of 60 weight% sample, and we can see some porosity there. And this is the microstructure of 80 weight% sample. So as you can see that there is a difference from 68% to 88%. Since the solid loading is high and also there is considerable grain growth, the microstructure looks good, even better in 88%. So I would like to conclude this by saying that DLP stands out for its precision and efficiency, and this technology is less dependent on molds and indirect tooling compared to slip casting, or it make more adaptable, and it reduces the time needed for design modification. So this is what I have done for a short while. And I would like to thank SEDAX's Additive Manufacturing Center, IIT Chennai, for permitting me to carry out this research work. And also, I would like to thank Dr. John Kennedy sir for helping me for finding out the phases which has formed and the SEM analysis. We are thankful to the organizers of this conference and Indian Ceramic Society Tamil Nadu chapter and IITM for allowing us to do this presentation here. Thank you so much.
Thank you so much for your talk. We might have time for one urgent question, but time is off. Yes, please go ahead.
This overexposure of light,
yes,
what is the problem will come?
Overexposure, sometimes overexposure can lead to the dimension may not be proper. So what we may not get what we decide. Sometimes, suppose if you are preparing a porous structure, the pore of that particular structure won't be exactly, or we may not be able to get an exact pore size as that of what we decide. So that is the due to overexposure, it can happen. The dimension can change.
Thank you once again for your talk. So maybe we can take a picture here. So there is one more question. Yes, please go ahead. Yes, one last question.
Yeah, nice work, Aishwarya.
Thank you.
I just wanted to ask, what is the difference between two loadings in viscosity of the slurry?
Viscosity, you are asking about...
Have you measured viscosity of the composite? After
I still didn't measure the viscosity. First of all, we wanted to try whether it is printable or not, even after higher solid loading.
So
with our machine.
Okay. Both were free flowing?
It's considerably higher viscosity than that of, for example, 88% has considerably higher viscosity than that of 68%. Yeah.
Okay. And how much layered structure you printed?
230, 230 micrometers.
And what was the thickness of each layer? Sorry.
Thickness of each layer is 50 micrometers.
50 micrometers.
Yeah.
And resolution of the printer was?
So can we continue the discussion at the lunch? So at the
lunch
lunch we'll
time
have sufficient time to discuss, okay? So thank you once again for your talk. Let us just take a picture here together. So you might have a memory on that. Thank you for your talk. So with that, let me just conclude the SPARC sponsored session on additive manufacturing of advanced ceramics. Thank you for all the speakers and for the contribution and discussions. We head now for the lunch break, and please come back to the technical session after the lunch. Thank you.
Thank you. So we will start with a first inviter talk coming from Denmark, and it will be dedicated to the optimization of ceramic slurries for additive manufacturing of high-performance solid oxide cells. So please.
Thank you, Professor Bernard. And good afternoon, everyone. My name is Venkata Karthik. I'm coming from the Technical University of Denmark, and I'm actually an alumnus of IIT Madras. So it is a very nice moment for me to come back here and give a talk. And today I will be talking about optimization of ceramic slurries using open source additive manufacturing to enable high performance solid oxide cells. I'm the group leader of additive manufacturing, materials and process development activities at the Technical University of Denmark that's located in Copenhagen. We are a small country with about 6 million people. And this work is in collaboration with Department DTU Energy, and I'm coming from the Department DTU Construct, which stands for Civil and Mechanical Engineering. All right, so let's begin with the working principle of solid oxide cells. Solid oxide cells essentially can convert, can be operated in two modes and can either convert fuel into electricity, or they can convert electricity back into fuel. And solid oxide cells, when operated in SOFC mode, typically have very high efficiency. And this is what makes them a very good candidate for power to X applications, where you have renewable sources of energy that you can convert into hydrogen or other sources that you can store and later reuse by reconversion back into electricity. There are many applications of these solid oxide cells, and they're quite an exciting area of development in the last decade. And more recently, there have been efforts to see if these solid oxide cells can be pushed into aerospace applications, where the efficiency of solid oxide cells would be really excellent. But right now, they don't have the necessary power density to do so. So what are the components of a solid oxide cell? It's essentially this yellow band, which is the electrolyte, and on top of that you have an electrode, an oxygen electrode and a fuel electrode, so an anode and a cathode. And then the only way to increase the effective surface area is to stack these things one on top of the other. And the commercially relevant way to do that is to stack them with metallic interconnects. The efficiency improvements using solid oxide cells are often realized when you operate at very high temperatures. And you need to have good mechanical performance at these temperatures. And having these metallic interconnects serves the purpose of thermal management and mechanical strength in these structures. But unfortunately, these interconnects form about 75% of the weight of these stacks. So right now, the technology is limited by this. So our idea was that essentially this fuel cell is just a layer. It's a layer with two sides. So what if we could create two sides in 3D? And there is a mathematical formulation of that. It's called periodic minimal surface. As you can see here, it's a gyroidal structure where you have two subvolumes separated by a layer. So if we think about the layer as an electrolyte and then the two sub-volumes as being the anode side and the cathode side, what you see here can look like a fuel cell if it is functionalized correctly. And we wanted to test this idea. And in our group, we have a philosophy of building open systems. We have heard talks from those making industrial systems today, some excellent use cases as well of industrial AM systems for ceramics. The reason we decided to develop our own system is because it gives us the flexibility to play with different materials. It gives us the flexibility to tune the process, to change mechanical components or change the software that is behind the process in order to get better results. And the technology that we are talking about here is called VAT photopolymerization or mask projection VAT photopolymerization, also called DLP, as was introduced a couple of times today. And the methodology is simple. You have a thin layer of photoactive material that you project UV light onto with a certain wavelength and a certain shape. And this cures the material locally, and then you repeat the process layer by layer. What we can do in our system that gives us an advantage is that we can play with the software side because we are in full control of the software and the hardware in order to apply computer vision algorithms like anti-aliasing in order to correct for rough surfaces or to get the precise feature definition so that we can get closer and closer to what the DMD mirrors or the projector can actually project onto the component. And the principle is that you start with a slurry that has the ceramic particles embedded inside it. And then when you cure it, it's only the photoactive photopolymer that cures. And then the slurry particles are, or the ceramic particles are frozen in shape. And in order to create a successful print, there are two very important things. The first thing that you need to consider is what is the cure depth. And in this morning's keynote, we heard a little bit about this. Essentially, the cure depth is the depth of penetration of the light into the photopolymer based on the amount of energy that you put into the system, the amount of light intensity that you put into the system. And you want to have a cure depth that is reasonable. You don't want the cure depth to be too large. Then you sacrifice on resolution, and you're probably over curing. Also in the XY dimension, not just the Z. And at the same time, you want to ensure that you're curing at least more than a layer thickness so that you get a bonding between an existing layer and the previous layer. The second thing you need to think about when you have a ceramic slurry is the viscosity of the slurry. The viscosity plays a very important role because depending on your system design, you want to have a slurry that has a lower viscosity and can flow in order to create space for the part to separate from the membrane. So here is an example. Yeah, here is an example where you can see the sample in contact with with a flexible membrane, a flexible and transparent membrane. And once you cure the material, there is a little bit of bonding between the membrane and the part. This occurs because you have local pockets of vacuum due to shrinkage during the photopolymerization process. And you need to break this vacuum somehow. So if your slurry is too viscous, then you do not have a good way to break this vacuum, and therefore you will fatigue your membrane and create defects. An example of that is shown here, where we were trying to figure out how to print this material for quite a long time. until we looked at the viscosity and figured out that by changing the volume percent just slightly, we could be down in the viscosity just enough that you get good printability from this material. Then once you have some printability, you need to do a heat treatment for which we did a TGA analysis, TGDSE analysis, and then here you see the sintering and debinding curves that we used. And so what we essentially did is we looked at first optimizing the green parts that come out, and then when we started sintering them, we also found cracks in these samples. And then we realized that, of course, these cracks are occurring because of sintering stresses or shrinkage stresses that are coming from the design itself. Then we did a redesign and then created a new concept with a cylindrical structure. And here you can see that these are X-ray CT scans. And you can see that there's cracking in these square type designs or cuboidal type designs, but we could completely eliminate those cracks in this cylindrical design, where we also introduced chamfering and beveling into some of the corners so that the shrinkage stresses are reduced. So after about 2 years since we first had the idea, we were able to get fully dense parts that were without any cracks in different designs with an optimized process. And then on the right side bottom here, you can see a CT scan of the component where we segmented the two volumes, each in one color. So then you have these two independent volumes in this material, where on one side you can create a cathode and on the other side you can create an anode, and the walls are fully dense and they have a good microstructure, and you also have a wall thickness of about 140 micrometers, which is quite good. Commercial electrolyte thicknesses are around 200 micrometers. So this is in all respects looking good. Then we looked at process repeatability and stability because we wanted to make sure that we can repeat this and that we have a process that can be stable. And indeed, after the optimization of both the slurry and the manufacturing, then we can repeat this again and again to get the same result in linear shrinkage and in density of the parts, both the green parts and the sintered parts. So what we developed is a new concept. This we call it a shell-supported solid oxide cell. Essentially, instead of having metallic interconnects, you're having the outer shell of the of this unit as the supporting layer, whereas the inner surface is active area that you can coat with whatever you want. So these the typical state-of-the-art electrolytes themselves, they have quite a low stress under compression that they can take. But having this outer support, when you increase the thickness of it, then you can get something that is mechanically quite resilient. That means you can apply a large amount of load on it. In our case, we applied 10 kilograms of load to create a sealing while doing the fuel cell tests. So now we have this structure, and we need to get the anode and the cathode. And the way that we do that is by injection of a slurry into the anode side, anode volume, and then calcine it so that it forms a thin layer and gets stuck. And then we do the same thing on the cathode side. And when we do that, we are left with something that looks like this, where on one side you have a nickel oxide via Z, and on the other side you have a LSM via Z, the anode and the cathode. And then we put that into a fuel cell test setup. Surprisingly, or not so surprisingly, nobody has tried this kind of a fuel cell before. So all the test setups were not really made for something that goes vertically upwards. So all the gas flow that is in existing setups was just created for 2.5D or very thin structures. So we came up with an idea where we put platinum paste on this, sintered it and created a wall so that the gas would flow in and up so that we are able to test it. And then we could see that the cell was then functioning. So we converted the horizontal flow into the vertical flow, and then we could see that the cell was functioning as it was supposed to. And here are the results of the test. Essentially, the cell has good galvanostatic stability, about 1.7 or 3% per 1,000 hours in the reduction in the voltage. And it also has good dynamic performance, so you can switch from one mode to the other quite well. So if we then take the weight of this fuel cell without any of the interconnects, and you compare that with a stack that has the interconnects, then you can see the specific power at the high operating temperature, where you get higher efficiency, is actually about 10 times in volumetric power density and about 8 times in specific power density. So this is quite a good fuel cell. So for the first time, we have come up with a fuel cell that has both high efficiency but also high power density. And that could open up this field for more applications like aerospace. And as a future outlook, we want to scale this up. We got selected in an accelerator program, about $700,000 US in funding to make a company out of this. And we have already submitted the patent and the publication related to that, and we are awaiting review. So in the future, we want to take this concept and expand it in at least 2 dimensions, XY, so that we can get something that is that has higher output, so larger power capacity. It will be space efficient and customizable, but thermal management would still be an issue. So that's something we are working on right now. So with that, I will say thank you very much to the Sierra Ferrous organizing committee for inviting me, and thank you all for attending, and thanks to my collaborators for working on this project.
Thank you very much. So the talk is open for some question. Okay, maybe I can start.
Yes.
You infiltrate your 3D printing part with the compound dedicated to anode and cathode.
Yes.
Is there any volume shrinkage during the sintering? I mean, because you imprinted different materials.
Mm-hmm.
Is there any difference of thermal behavior during the sintering?
Yes, if we sintered it all to full density together, it would be, but we sinter the monolith, we call it the monolithic electrolyte to full density, and then we apply these coatings, and then the temperature at which you need to calcine them is much lesser. It's only 900,000 degrees, so it doesn't affect the main electrolyte. So then you form a coating. In fact, what we found was that you can apply some coating, sinter it, and then apply some coating, take some pressurized air and blow it through, so only the coating is left over, and then you measure the weight, then you see some milligram change, and you can do that for as thick as you want the coating to be, according to the optimal thickness of the coating.
Okay.
So it's a robust method, I think. Yeah.
Another question? Yes, please.
Yeah, good question. Actually, that's something that will be an issue as we are scaling up. We yes. Yeah, so we have some we have some ideas on how to deal with it, but we are not sharing them right now. Yeah.
Sir,
Definitely.
after sintering, like if cracks develop, like NIO wise did, after sintering, many a times crack develops. What is the fracture strength?
So the interesting thing about our design is that it's actually supported by the outer shell of the electrolyte. So when we apply stresses on it, and we have some simulation models that show us this, when we apply some stresses on it, we can see that it is the outer shell that's taking most of the load. And this is why this concept works. So if we are even more smart about designing the structure, that the electrolyte that's connected to the walls is actually tapering out into a thicker region, then you would have a very even distribution of majority of the stress on the outside and no stress concentrators on the inside.
So, sir, you want to tell that like your electrolyte material and interconnect material are combined together in some way?
Yes, for sure. Like we have applied it. We have applied the anode and the cathode.
Okay.
Yeah. So
in the powder structure.
I propose to speak during the coffee
Yeah,
break because
sure.
it's time to close this first talk. Okay.
Okay.
Yeah,
Thank you so much. Thank you again for your nice talk. Okay, we can welcome the second talk. This is also an invited talk, and from India, and the title will be Ceramic 3D Printing by DLP Technology, and it will be given by Professor Ramachandra, from India. Thank you. So please.
Thank you, Professor, for your kind introduction, and good afternoon for everyone. So, yeah. So my name is Davanesan. I'm coming from. Yeah. So my name is Davanesan. I'm coming from Tava Technical Ceramics, Coimbatore. So today I'm going to talk about ceramic 3D printing developed by our partner from South Korea, the company name called 3D Controls. So this is not going to be too much technical. This is going to have what kind of product we have for 3D printing machines. So just a quick introduction about me. I did my master from IIT PhD from the college, the next speaker from, and also from DT Energy, where I did my PhD in 2014 from the previous speaker from. And also I worked in various industry, and currently I'm working on my own industry. So before going in detail with the 3D printing, just I want to give my motivation, why you are going to 3D printing. So just I'll go a little bit about how that advanced ceramics develop in India and globally. So everybody aware that these are the material used for various advanced material application, as well as where it is used mainly in electrical electronic industry and automotive and machinery and environment, as well as medical. And the primary material is alumina, titania, and zirconia. These are major material used for advanced ceramics, as well as used for various applications.
So regarding to that share, how it is, the advanced ceramics working, more than 50% is working from electrical and electronic industry and automobile a little bit, and machinery and environmental applications. Coming to the market share of Asia market, 40% come from Asia market and remaining 60% coming from Western countries. So coming to India, so we are only contributing less than 1% towards advanced ceramic material manufacturing. Since we have the population number 1, still we are a long way to go. However, the recent year we are growing like 15 to 20% growth rate in the advanced ceramic material manufacturing technology. Because of there is a lot of many projects coming up with related to semiconductor, EV, and medical devices, and that's the reason we are growing a little faster compared to other countries. So one of the big challenges still we are lacking with the technical limitations, since if you compare to Western industry, they are still far ahead with using various type of technology, adapting to the developing advanced material. As well as since we are starting now, last 10 years, we are starting now, still long way to go to compete with the global player. So that also we have a lot of difficulty to compete with, since we are looking for the market, not only India, we are looking for the market globally. So that also one of the things we need to focus now. As well as still we need to develop the skill required for making these advanced materials. Still the government is putting a lot of effort to develop the skill gap, to reduce the skill gap. So considering all this, the many projects is coming in, particularly the semiconductor mission. India government is investing more than $10 billion as a subsidy, so that they can bring up global player to make various advanced material related to semiconductor, so on. So by the note, we are started collaborating with the Korean companies so that we can bring new technology to us, so that we can make different ceramic material that can be used for semiconductor, medical, or energy applications. So that the note, we'll start with why we are going to use 3D printing rather than other technology, where it is the 3D printing is more applicable. If you consider the customer is looking for small quantity with more precision is needed, so currently they are using the process called SIM process. The SIM process is ceramic injection molding. The ceramic injection molding even cost for tool making costs, as well as a lot of machine is required. Whereas this 3D printing easily replace this technology, so that it is easily fabricable, as well as you can quickly make within day rather than waiting for 2 weeks, 3 weeks to make the tool, and sinter it will take more than a month. So as I mentioned earlier, this is a wide range of area where this 3D printed material can be used. Aerospace industry can be used, electrical electronics, as I mentioned, energy, and jewelry. Jewelry is one of the most demanding application for our 3D printing machine. As well as the machinery, any critical command require the tolerance of 20 to 30 micron without any machining. So 3D printing is one of the alternate. So the 3D printing involve 5 different processes. First we'll make the 3D printing modeling, then slice as per the layer thickness. The layer thickness varies from 20 to 100 micron. Then we'll go for 3D printing. Then after 3D printing, we'll go for cleaning the surface, that is washing with our liquid, so that we can get an exact surface. Then we'll go for debinding and sintering process. Finally, we make the component. So our technology involves this various technology involved making 3D printing by digital laser processing. Our process is like top-down method, so that component will be stable, as well as it is curable with the open atmosphere. Whereas there is other technology developed where the printing happen bottom to top, there is some slugging will happen. So that's the reason we are going for top-down method. So just to introduce our machine is very small one, like within size of within room you can manage every system. So our build-up area is 125 into 65 into 45 area, and our, as I mentioned, our layer thickness varies from 20 to 100 micron, but typically we use 50 micron as a optimal layer thickness. And we will use the wavelength of 405 nanometer, and the pixel also like 20 micron accuracy. So here there is a video, is not playing anyway, just I'll play the video after that by presentation. This is, I just will list out what are the steps involved making the 3D printing. First we'll print each layer like 20 micron or 50 micron, then then the UV laser will pass on it, then it will cure it like this happen, like Dr. Venkat mentioned that the similar process we will follow, but our method is drop-down method. So this, for making this component, we will spend like more than an hour, so we can make up to 40 thickness. So this is a typical size of our machine. Like you can keep it in your room, you can print it, and it need less electricity also. And it is you can take it wherever you want. It is easily movable, as well as it's very safety, and yeah, because of it is not harmful to open atmosphere. And this technology is patent about our design. So you have our 4 patents related to our machine. And as well as, because since we are using like top-down method, the cleaning process is involved. If you are using bottom-up method, there is no cleaning is required. Here we need cleaning, so we have a special device where the cleaning operation will happen, so that we'll have the accurate component after the cleaning process. And we are offering along with the 3D printing, like with the cleaner, furnace, as well as the polishing unit if it is required. So this is again saying about what are the components integrated with our systems. I'm not going in detail. This is just an output, how it look like 3D drawing, how it is actual output after that printing. So we have the accuracy of like the roughness between 40 to 50 micrometer. And this is our reference material. Currently we are working on 2 material, as well as we are adding another 2 material like ZTA, then Yttria, as well as we are going for non-oxide also, aluminum nitrate, silicon nitrate, silicon carbide also we are going. So we are achieving up the density of theoretical density up to 99%, whereas in alumina we are getting up to 98%. And the strength also we are getting quite good strength, almost 800 megapascal with zirconia and 350 megapascal with alumina product. So our strength is more sufficient for whatever the application demanding. This is indicated, we outlined how the yield, and how long will take it to print each samples. I list out the zirconia as well as alumina. So hardly will take like more than an hour if the thickness is, if the criticality is there, it will take more than an hour, otherwise we can print it within 30 minutes. If example, will take the ring, it is height of 6 so we can print it within 42 minutes with the accuracy of 25 micron. So even we put out how long is there any failure out of 310 cycle, we failed only 4 times. That means the yield is more than 90%. So if you have small room size like 20 to 15 feet size, you can fit our machines comfortably, and you can play around. So currently we sold a couple of machines for jewelry making. They are running at home and they are selling, and they are making zirconia paste jewelries. So if you want to expand, and you can expand within the same size, you can put the 3 machine, and you can manifold the production capacity up to 6 times. So again, there is a video is not playing here. I will play later. So just I'll take the case study of how it is compared to other process made by the dental teeth. So currently in India, so many dental blank is made, dental crown is made by CNC milling, almost more than 95%. Only few people are using 3D printing. You can see that roughness, roundness This 3D printed is more accurate compared to CNC milling. So almost it is 120 micron is coming, whereas 3D printed material giving accuracy less than 60 micrometer. So Europe started using heavily. So we sold many machines in Europe. They are using more than 20% going for medical application, mainly for dental crown making. If you take another case study, this is a company from Europe again. They are making equipment for NTA, equipment for secondary batch testing. Earlier they used ceramic injection molding printed component. It is failed within few cycles. So we developed for them, and it is working more than 1 year without any breaking. And currently we are setting separate plant and are supplying to them. This is like another unit you put it to manufacture to the companies, and we are selling it out. So this is one of the another good example where we are producing the mass productions. So not like we are not only making the lab scale, we are come to the level where mass production is happening. So we have innovation center in Seoul in Korea, where we have 5 machines dedicatedly working for producing mass scale for our global customer. In regard to the strength in different direction, because you can 3D printing can be printed any direction if you want. So just we compared how our mechanical strength varying in different directions. So you see that customer 1, customer 2 and 3D control. So there is no variation in the mechanical property if you are changing your printing direction of your component. So we have some kind of system with that, not only slurry in the machinery as well as the blade system, that will give uniform mechanical property if you are changing your printing directions. This is our global reference where we have supplied our samples, where we get the request and supplied samples for 3D printing. So we printed more than 180 company globally, and even including India. And we have started mass production for them, more than 5 to 6 customers globally. So we got good response for our printer, and yeah, so we are free to do samples for you. If you have any requirement, if you have any criticality, if you want any critical product, just send us. We'll make the product for you. We'll send free of cost to understand our process, our product quality. So this is how it is 3D modeling between and really 3D printed samples. Just to compare, again it's similar to them, even better to them. Again the ceramic part after sintering. So we can make the various components. Any kind of intrication is there, you can make it with a simple printing. Like lizards also we printed. You can, if you have your time permits, please to our visit stall. It is located in the corner of the cafeteria. So that is the end of my presentation. If you have anything related to 3D printing, please come and visit us. So I'll play quickly one video. It is missing from the presentation. Yeah. Yeah, thank you very much.
Thank you very much. So we have time for some questions. Are you only focused on alumina and zirconia product, or you can produce other types of?
Yeah, currently alumina. So currently we have developed a system for alumina, zirconia, ZTA, and other than that we are working on yttria and silicon carbide and silicon nitride, aluminum nitride. That is going to come up in maybe next year. We are developing the slurry as well as systems.
Okay.
Yeah, thank you very much.
Thank you. Another question? If not, thank you again. So we'll welcome the last talk of this session dedicated to additive manufacturing, and the title will be Optimizing DLP for High Fidelity Ceramic Micro to Macro Architectures.
Good afternoon everyone. Myself Sandeep Kumar SG, currently studying BTech Mechatronics and Automation in IIT Chennai. Here I am going to talk about optimizing digital light processing for high fidelity ceramic lattice patterns under guidance of Dr. Raghukiran Nadumpally, IIT Chennai. And this is the contents. Here we will be speaking about additive manufacturing, ceramics, and my experiment in printing ceramic parts using DLP, and I have made some mechanical testing and did some simulation studies also. Well, coming to additive manufacturing, it is a manufacturing process where the part is printed by layer, and the main advantage over additive manufacturing is we have more design freedom and we can get a solid part which we are imagining in our mind. And this is the steps involved in additive manufacturing, from reverse engineering, making a 3D CAD model, converting it into STL file conversion, and setting up the machine and getting the green part and doing post processing, and we will get the final part. And the different types of additive manufacturing includes FDM, SLA and SLS, and also material jetting things. While coming to VAT polymerization, there are three types. SLA, it means stereolithography, digital light processing, and LCD based. And here I am going to mainly focus on digital light processing. I am not going to speak much about digital light processing because all the authors before me were speaking about digital light processing. So I will be directly speaking about the principle of it. Here, the first layer is printed when the bed comes to the layer height of the VAT. Here the layer height which I have been used is 50 microns, and after adding each and every layer we will be getting the part, and after post processing we will be getting the final part. And while coming to ceramics, as we all know, ceramics are inorganic and non-metallic compounds which has unique properties which polymers and metals doesn't have. And there are some technical ceramics like zirconia, alumina and silica carbide, and here I mainly focus on aluminum oxide since I have used aluminum oxide in my study. Aluminum oxide is a key ceramic material which is known for its high hardness, excellent electrical insulation properties and resistance over wear and corrosion. And the application of alumina is, since it has high electrical insulation property, we can use it as in any fins, in any processors or computers, and we can use it in mechanical components, and due to its dielectric property we can use it in aerospace defense, and as we all know alumina is a biocompatible material, we can use it as a biomedical applications also. And these are the available ceramic manufacturing process, and first two are traditional way like cold pressing and slip casting. and rest comes additive manufacturing like extrusion, binder jetting, and FDM. This FDM pick I took from Zetamix and SLA from Lithos. But the challenges which we faced in current traditional manufacturing techniques, like we can't get, it is impossible to manufacture a complex structures like lattice patterns, but it is possible using SLA techniques, but it poses high production cost. So in this research, I will be trying to overcome all these four challenges, and this is my experimental work. I just selected a normal standard photopolymeric resin, which is openly available in market, and added alumina powder and did ball milling with 300 RPM. And I have optimized the printing parameters of the machine so that this slurry we can get this slurry can be printed. And right corner you can see the green body, and after debinding and sintering at 1550 degrees Celsius, we can see the final part at bottom. And after doing TGDT analysis of my slurry, I found out all the binders and solvents are removed out during temperature during 400 degrees Celsius to 500 degrees Celsius. So I kept I hold it on 500 degrees Celsius for 1.5 hours, so that all the binders and solvents are removed and only pure alumina parts are there. And I have sintered this part at 1550 degrees Celsius for 4 hours, so that there will be more grain growth and we will get a high mechanical properties. And this is one of the structure which I have printed. At left we can see the CAD model, and next we will see the green body at the top and the sintered body at the bottom. And at the rightmost you can see the optical microscopy images of the green and sintered body. And this is another structure, triangular lattice. And here you can see a same green body, sintered body, and optical microscopy of these images. And I have done SEM analysis of the green body. Here you can, at left picture you can see the visible layers, and at the middle and the right picture you can see some of the agglomerants and some impurities. These agglomerates we can make it as more homogeneous further milling, and it can be done in future. And this is the sintered SEM image of sintered body at 1550 degrees Celsius. Here we can see all are closely packed and there is a good grain growth. But since it is like still the binders are removed and some places were kept porous, it should be optimized further. And I have done simulation studies, compression studies in simulation for both the structures. And I have done a compression test in real time also. And here we can see the comparison between the simulation and the experimental compression strength. And as of now, the results got from simulation and compression are almost same. Only there is a high difference when the parts get failed during 8 Newton for triangular lattice and 22 Newton at hexagonal lattice. Since these are lattice patterns, I got only like very less strength, since it is around 90% porous, these structures and all. And in future prospects, we can use this technology for aerospace and defense and dental and medical implants, since alumina is a biocompatibility material, and we can use this for filtration media and catalyst supports. And in conclusion, in this research, I have used 88% of ceramic loaded slurry, optimized the printing parameters to make the slurry get printed. Since it is 88%, the slurry will be more thick and we can't get printed as easy. And as easy as printing a polymer. And debinded and sintered at 1550 degrees Celsius for 4 hours. And studied the surface morphology of green body and sintered body using SEM analysis, and did compression test for 2 different lattice structures in UTM machine, and did simulation of the compression test of the same, and compared the simulation test and real-time results. I want to acknowledge Sadaxis Advanced Materials and VIT Chennai for their technical support for this research, and I want to thank Dr. Ravikiran Nadumpalli for his guidance during my research work. And I thank IIT Madras and their committee members for organizing this conference at their best. And I thank Indian Ceramic Society for this wonderful opportunity. Thank you.
So we have time for some questions. Okay, you didn't mention, or maybe I missed the information, the volume shrinkage occurring during the green body to the sinter body. What is the volume shrinkage?
Volume shrinkage. Volume shrinkage I got around 30% in x-axis, x and y-axis, and 20% in z-axis.
Okay. Okay. Thank you. Another question? Okay. If not, thank you again. And I would like to thank all the speakers for this session. So this session ends, and I would like also to thank you for your kind attention. Thank you very much.